About 29 million light-years away from Earth, there is a galaxy that changed everything scientists thought about space. It is called the Sombrero Galaxy, and it looks like a giant hat floating in the dark universe. What started as just a bright light in the sky turned into one of the most confusing discoveries in astronomy. This galaxy has a huge ring of dark dust that shines in a strange way, and inside it there are about 2,000 clusters of stars, each one with hundreds of thousands of suns. But here is the part that keeps scientists awake at night. In the center of this galaxy, there is a black hole that weighs 1 billion times more than our Sun. Get ready to fall asleep while you listen to this video and discover why this hat-shaped galaxy can change everything you think about the universe. Subscribe to the channel. Leave your like and comment from which part of the world you are watching. Get comfortable and relax. Let's begin. Imagine looking up at the night sky in the late 18th century, with only rudimentary telescopes at your disposal, and suddenly spotting a peculiar fuzzy object that doesn't behave like a star. This is exactly what happened to French astronomer Pierre Méchain in May 1781 when he became the first person to document the celestial object we now know as the Sombrero Galaxy. The discovery would soon become a significant milestone in our understanding of the universe beyond our solar system. After Méchain's initial observation, his colleague and fellow astronomer Charles Messier included this mysterious object in his famous catalogue as M104. Messier was compiling a list of fuzzy celestial objects that might be confused with comets, and the Sombrero Galaxy became the 104th entry in this influential catalogue. At the time, neither Méchain nor Messier could comprehend the true nature of what they were observing. The technology of the 18th century simply didn't allow them to see that this patch of light was actually a massive collection of billions of stars, a galaxy in its own right. The distinctive appearance that gave the galaxy its popular name wasn't recognised until much later. It was in the 1840s when William Parsons, the third Earl of Rosse, commonly known as Lord Rosse, observed the galaxy through his massive 72-inch reflector telescope called the Leviathan of Parsonstown. Lord Rosse noticed the galaxy's peculiar shape, with a bright central bulge surrounded by a flat, extended structure. He described it as resembling a hat, specifically like the broad-brimmed Mexican sombrero, and the nickname Sombrero Galaxy was born. Throughout the 19th century, astronomers continued to study this intriguing object, but their understanding was severely limited by the technological constraints of the era. It wasn't until 1917 that the true nature of the Sombrero Galaxy, and indeed all galaxies, began to emerge. This was when astronomer Heber Curtis observed what appeared to be a nova in the Sombrero Galaxy. This observation provided some of the first evidence that these spiral nebulae were actually independent star systems far beyond our own Milky Way. The debate about the nature of these objects culminated in the famous Great Debate between Harlow Shapley and Heber Curtis in 1920. Curtis argued that spiral nebulae like the Sombrero were island universes, independent galaxies far beyond the Milky Way, while Shapley believed they were part of our own galaxy. This scientific controversy wasn't fully resolved until 1923, when Edwin Hubble measured the distance to the Andromeda Galaxy, proving conclusively that these objects were indeed separate galaxies far beyond our own. For the Sombrero Galaxy specifically, our understanding took a quantum leap forward with the advent of modern telescopes in the 20th century. When the 100-inch Hooker telescope at Mount Wilson Observatory was trained on the Sombrero in the 1920s, astronomers could finally resolve individual stars and see details of its structure. They confirmed its spiral nature and began to appreciate its unusual features, particularly the extraordinarily bright nucleus and the prominent dust lane. The advent of radio astronomy in the 1950s and 60s added another dimension to our understanding of the Sombrero Galaxy. Astronomers could now detect radio waves emanating from the galaxy, providing information about gas and other materials not visible in optical wavelengths. This multi-wavelength approach revealed that the Sombrero contained vast reserves of hydrogen gas and showed evidence of past periods of intense star formation. The true revolution in our understanding of the Sombrero galaxy came with the launch of the Hubble Space Telescope in 1990. When Hubble turned its eye to the Sombrero in 1994, it captured what would become one of the most iconic images in astronomy. The telescope's unprecedented resolution revealed the galaxy's structure in breathtaking detail, from the brilliant central bulge to the intricate patterns in its dust lane. These observations showed a complex and dynamic system with a population of globular clusters far exceeding what astronomers had expected. Scientists were particularly intrigued by the extremely bright nucleus revealed in the Hubble images. This provided some of the first strong evidence for the presence of a supermassive black hole at the center of the Sombrero galaxy. Subsequent observations using X-ray telescopes like Chandra confirmed this hypothesis, showing high-energy emissions consistent with matter falling into a black hole. The historical journey of discovering the Sombrero galaxy reflects the broader development of astronomy itself, from its humble beginnings as a fuzzy patch noted by Méchain and Messier, to the detailed multi-wavelength observations we have today. Our understanding has evolved dramatically. Each technological advance has peeled back another layer of this fascinating object, revealing new details about its structure, composition, and history. Today, astronomers know the Sombrero galaxy as M104, located approximately 28 million light-years from Earth in the constellation Virgo. It spans about 50,000 light-years across, about half the size of our own Milky Way, yet it contains roughly 1 trillion stars, comparable to our galaxy. Its distinctive appearance comes from our edge-on view of its disk and the prominent dust lane that encircles its bright central bulge. The discovery and study of the Sombrero galaxy exemplifies the patient, incremental nature of scientific progress. Each generation of astronomers has built upon the work of their predecessors, gradually assembling a more complete picture of this remarkable object. From a mysterious nebula to a fully characterized galaxy with a supermassive black hole at its center, our understanding of the Sombrero galaxy continues to evolve with each new observation and technological advancement. The hat-shaped structure, origin and composition. The Sombrero galaxy stands out among the billions of galaxies in our universe due to its distinctive appearance. When you look at an image of this celestial marvel, you can immediately understand why it earned its nickname. It truly resembles a wide-brimmed Mexican hat floating in the darkness of space. This characteristic shape isn't just visually striking. It offers astronomers valuable information about galactic formation, evolution, and composition. The hat-like appearance of the Sombrero galaxy is not an intrinsic three-dimensional shape, but rather a product of our particular viewing angle from Earth. We're observing this galaxy almost perfectly edge-on, at an inclination of approximately 6 degrees from our line of sight. This fortuitous orientation allows us to see both the galaxy's bright central bulge and its extended disk in a way that creates the Sombrero appearance. If we could somehow view the same galaxy from above or below, it would appear as a fairly typical spiral galaxy with a remarkably large central bulge. The brim of the hat is formed by the galaxy's thin disk, which extends roughly 25,000 light-years from the center. This disk contains the majority of the galaxy's younger stars, along with vast amounts of gas and dust organized into a subtle spiral pattern. Unlike the dramatic spiral arms seen in galaxies like the Whirlpool Galaxy, the Sombrero's spiral structure is more subdued and tightly wound. Astronomers classify it as an ESA-type spiral galaxy in the Hubble sequence, indicating a galaxy with a prominent bulge and tightly wound spiral arms. What really defines the Sombrero shape, however, is the dramatic dark dust lane that encircles the galaxy's central bulge. This dust lane appears as a dark band because it consists of dense interstellar material that absorbs and blocks light from stars behind it. The lane is approximately 700 light-years wide and contains an estimated 10 million solar masses of dust and gas. This might sound enormous, but it represents just a tiny fraction of the galaxy's total mass, which is estimated at 800 billion solar masses. The composition of this dust lane is particularly interesting to astronomers. Spectroscopic analysis reveals that it contains a complex mixture of materials. The majority is made up of tiny particles of silicates, graphite, and other carbon-based compounds including polycyclic aromatic hydrocarbons, PAHs, complex organic molecules that are some of the basic building blocks of life. Mixed with these dust particles are various gases, predominantly hydrogen and helium, but also including more complex molecules. When observed in infrared light, this seemingly dark band actually glows brightly, revealing it to be a region of ongoing star formation. The central bulge, the crown of the Sombrero, is one of the most massive and luminous galactic bulges known. It extends about 15,000 light-years from the galactic centre and contains predominantly older, redder stars that formed billions of years ago. The stars in this region orbit the galactic centre in a more random dot, three-dimensional pattern compared to the organised, planar orbits of stars in the disk. This bulge is so large and bright that some astronomers have suggested the Sombrero might actually be an elliptical galaxy in the process of accreting a spiral disk, essentially a galactic hybrid. At the very centre of the bulge lies one of the most massive black holes known in the nearby universe. This supermassive black hole has been measured to contain approximately 1 billion solar masses, hundreds of times larger than the black hole at the centre of our Milky Way. The interaction between this enormous black hole and the surrounding stellar environment likely played a critical role in shaping the galaxy's distinctive structure. What makes the Sombrero's structure particularly valuable to astronomers is how clearly delineated its components are from our viewing perspective. The dust lane is sharply defined against the bright background of the bulge, allowing detailed studies of dust composition and distribution. The clear separation between the older stars of the bulge and the younger population in the disk provides a perfect laboratory for studying stellar evolution in different galactic environments. The origin of this distinctive structure remains a subject of ongoing research, but several theories have emerged. One possibility is that the Sombrero's unusual appearance results from a past merger between two different types of galaxies, perhaps an elliptical galaxy and a smaller spiral galaxy. Evidence for this includes the unusually large bulge-to-disk ratio and the presence of extended stellar structures far beyond the visible disk. Another possibility involves the galaxy's evolution in relative isolation. Unlike many galaxies that show signs of recent interactions with neighbours, the Sombrero appears remarkably undisturbed. This suggests it may have evolved through internal processes rather than external influences. The massive central black hole likely played a significant role, potentially driving gas inflows that built up the central bulge while simultaneously regulating star formation through energetic outflows. The dust lane itself may have formed through a combination of gravitational effects and stellar processes. As stars age and die, particularly when they explode as supernovae, they eject material back into interstellar space. In a rotating galaxy, this material naturally settles into the plane of rotation, gradually building up the thin disk and dust lane we observe today. Advanced computer simulations of galaxy formation are helping astronomers understand how structures like the Sombrero develop. These models suggest that the particular combination of a massive central bulge with a thin, well-defined dust lane requires specific initial conditions and evolutionary pathways. By comparing these simulations with actual observations of the Sombrero and similar galaxies, scientists are gradually piecing together its life story. Studying the Sombrero's structure also provides insights into the distribution of dark matter, the invisible substance that makes up approximately 85% of the matter in the universe. By carefully measuring the rotation speeds of stars at different distances from the galactic centre, astronomers can map the total mass distribution, including the unseen dark matter. The Sombrero's well-defined structure makes it an ideal subject for such studies, through continued observation using increasingly sophisticated instruments. Astronomers are constantly refining our understanding of this celestial sombrero. Each new discovery about its structure and composition adds another piece to the puzzle of galaxy formation and evolution, helping us better understand not just this particular galaxy, but the fundamental processes that shape our universe. Now, peering even deeper into the heart of this majestic galaxy, we find something both fascinating and terrifying, a monster lurking at the very centre. The Sombrero galaxy harbours one of the most massive black holes ever detected, a gravitational behemoth that shapes everything around it. Unlike the relatively modest supermassive black hole at the centre of our own Milky Way, which weighs in at about 4 million times the mass of our Sun, the central black hole in the Sombrero galaxy is truly in a league of its own. Astronomers estimate that this cosmic giant has a mass of approximately 1 billion solar masses. That's 1,000 million times the mass of our Sun, compressed into a region smaller than our solar system. This staggering measurement places it among the most massive black holes known in the nearby universe. The first strong evidence for this monster came in the 1990s when the Hubble Space Telescope observed stars and gas near the galaxy's centre moving at extraordinary speeds. The only explanation for such rapid orbital velocities was the gravitational influence of an incredibly massive, compact object. Confirming the exact mass of this black hole has been a technical challenge requiring multiple lines of evidence. One approach involves measuring the velocities of stars orbiting near the galactic centre. Just as planets in our solar system orbit faster when closer to the Sun, stars orbit faster when closer to the central black hole. By carefully mapping these stellar velocities, astronomers can calculate the mass needed to produce the observed motion. Another technique examines the emission of hot gas swirling around the black hole. As matter falls toward the black hole, it heats up and emits X-rays and other forms of high-energy radiation that can be detected by space-based observatories like NASA's Chandra X-ray Observatory. What's particularly interesting about the Sombrero's black hole is that it appears oversized relative to the galaxy itself. Astronomers have discovered a general relationship between the mass of a galaxy and its central black hole, typically. The black hole accounts for about 0.1% of the mass of the galaxy's central bulge. But the Sombrero's black hole represents a much larger proportion, suggesting it grew more rapidly or efficiently than the black holes in most other galaxies. The origins of this enormous black hole remain somewhat mysterious. It likely began as a much smaller seed black hole in the early universe, perhaps formed from the collapse of a massive star or directly from dense regions of gas in the primordial cosmos. Over billions of years, this seed grew through two main processes: by consuming gas that fell toward the galactic centre, and by merging with other black holes during galaxy collisions. The unusually large size of the Sombrero's black hole suggests it may have experienced a particularly dramatic history of growth and mergers. Despite its enormous mass, directly observing this black hole is impossible because, by definition, black holes do not emit light. What astronomers actually observe is the effect of the black hole on its surroundings. The region immediately around the black hole, known as the accretion disk, consists of superheated gas and dust that emits intense radiation across the electromagnetic spectrum before crossing the event horizon, the point of no return. The Sombrero's black hole is currently in a relatively quiet phase, consuming matter at a modest rate compared to the extremely active black holes in quasars and other active galactic nuclei. Nevertheless, it still generates enough energy to create a detectable glow at the galaxy's centre. This relatively low activity level presents something of a puzzle. With such an enormous mass, one might expect the black hole to be generating more fireworks. One theory suggests that previous periods of intense activity may have cleared out much of the nearby gas, leaving little fuel for the black hole to consume. Another possibility is that the black hole's energy output is regulating itself through a feedback process, when the black hole becomes very active. The radiation it produces pushes away nearby gas, cutting off its own fuel supply until that gas can cool and fall back toward the centre. The influence of this supermassive black hole extends far beyond its immediate vicinity. Its gravitational pull helps shape the orbits of stars throughout the galaxy's central bulge, while the energy it releases during active periods can affect star formation across much larger regions. Some astronomers believe that the energy output from the black hole in earlier, more active phases may have played a key role in giving the Sombrero galaxy its current appearance, perhaps by heating and pushing gas outward from the central regions, limiting star formation in those areas. Studying the Sombrero's central black hole isn't just important for understanding this particular galaxy, it provides crucial insights into how these cosmic titans form and evolve throughout the universe. By comparing the properties of black holes in different types of galaxies at various distances, and therefore various points in cosmic history, astronomers can piece together the life stories of these enigmatic objects. Advanced computer simulations are helping scientists understand the complex dance between supermassive black holes and their host galaxies. These models suggest that the growth of the black hole and the evolution of the galaxy are intimately linked through processes that regulate each other. During a galaxy's formative years, abundant gas can fuel rapid black hole growth and intense star formation. Later, energy from the active black hole can prevent gas from cooling and forming stars, leading to the relatively quiet state we observe in the Sombrero galaxy today. Recent technological advances are opening new windows into the study of supermassive black holes like the one in the Sombrero, but the development of event horizon-scale imaging, demonstrated by the famous first image of a black hole in the galaxy M87, offers the tantalizing possibility of someday obtaining a similar direct image of the Sombrero's central black hole. Meanwhile, gravitational wave observatories are beginning to detect the ripples in space-time caused when black holes merge, potentially allowing astronomers to trace the growth history of these objects. Moving outward from the galaxy's central black hole, we encounter another fascinating feature that makes the Sombrero galaxy truly exceptional: its globular clusters. These densely packed spherical collections of stars orbit the galaxy like a swarm of bees, forming a spectacular halo that extends far beyond the visible edges of the galactic disk. What makes the Sombrero's system of globular clusters so remarkable is not just their beauty, but their sheer abundance. This galaxy hosts approximately 2,000 globular clusters, an extraordinary number that dwarfs the Milky Way's modest collection of about 150. Globular clusters are among the oldest structures in the universe. Each one contains hundreds of thousands to millions of stars, all formed from the same cloud of gas and dust at roughly the same time. The stars in the Sombrero's globular clusters are estimated to be between 10 and 13 billion years old, making them nearly as ancient as the universe itself. These stellar fossils provide a window into the early history of the galaxy and the conditions present when these stars formed. The unusually rich population of globular clusters around the Sombrero galaxy has prompted astronomers to question why this particular galaxy developed such an extensive system. One theory suggests that the Sombrero may have cannibalized many smaller satellite galaxies throughout its lifetime, accumulating their globular clusters in the process. Another possibility is that the unique conditions during the galaxy's formation, perhaps an unusually dense region of the early universe or a particularly efficient star formation process, led to the creation of an exceptionally large number of these clusters. What makes these clusters so valuable to astronomers is their composition. The stars in globular clusters formed very early in the galaxy's history, before the interstellar medium had been enriched with heavy elements produced by previous generations of stars. As a result, these stars are primarily composed of hydrogen and helium, with much lower abundances of elements like carbon, oxygen, and iron compared to younger stars. By studying the chemical composition of stars in different clusters, astronomers can piece together the chemical evolution of the galaxy over time. The distribution of these globular clusters also tells an important story. They're not randomly scattered around the galaxy but show distinct patterns in their arrangement. Many form a spherical halo centered on the galaxy's core, while others seem associated with the disk component. This distribution provides clues about the different formation mechanisms that built up the Sombrero galaxy over cosmic time. The clusters in the spherical halo likely formed very early or were acquired through mergers with smaller galaxies, while those associated with the disk may have formed slightly later during the assembly of the galactic disk. Observing individual stars within these distant clusters is a challenging technical feat, even with the most powerful telescopes. The clusters appear as fuzzy patches of light rather than collections of individual stars. To study them in detail, astronomers use techniques like spectroscopy to analyze the collective light from all the stars in the cluster. This allows them to determine the cluster's overall age, chemical composition, and motion through space. The Hubble Space Telescope has been particularly valuable for studying the Sombrero's globular clusters, allowing astronomers to catalogue and characterize hundreds of these objects. The motions of these globular clusters serve another crucial scientific purpose. They act as tracers of the galaxy's gravitational field, allowing astronomers to map the distribution of both visible and dark matter. By measuring how fast clusters orbit at different distances from the galactic centre, scientists can calculate the total mass contained within those orbits. These measurements consistently show that there's far more mass than can be accounted for by the visible stars, gas, and dust, providing compelling evidence for the existence of dark matter extending far beyond the visible galaxy. Colour variations among the Sombrero's globular clusters have revealed another interesting aspect of their history. While many appear reddish, indicating they're composed entirely of very old stars, others show a bluer tint that suggests more recent star formation. This colour bimodality, the presence of two distinct populations, is seen in many galaxies and likely reflects different formation epochs or origins for the clusters. The red clusters may have formed along with the original galaxy, while the blue ones might have been acquired later through galactic mergers. The Sombrero's globular cluster system continues to yield new discoveries as observational technologies improve. Recent studies have identified a small number of ultra-compact dwarf objects orbiting the galaxy, entities that appear to be either extremely large globular clusters or the stripped-down nuclei of small galaxies that were consumed by the Sombrero. These objects occupy an interesting middle ground between star clusters and dwarf galaxies, potentially providing insights into how these different types of cosmic structures relate to one another. While the globular clusters form a majestic halo surrounding the Sombrero galaxy, perhaps the most visually striking feature when we look at images of this celestial object is the dramatic dark dust lane that cuts across its bright central bulge. This prominent feature gives the galaxy its distinctive sombrero-like appearance and contains a treasure trove of information about the chemical processes occurring within galaxies, appearing as a stark black band against the luminous background of billions of stars. This dust lane is actually a complex ecosystem of matter with a fascinating chemical story to tell. The dust lane isn't actually a void or empty space as its dark appearance might suggest. Rather, it's an incredibly dense region filled with interstellar dust particles, gas molecules, and complex compounds that absorb and block the light from stars located behind it. This absorption is what creates the striking visual contrast that defines the Sombrero's iconic profile. The dust lane forms a nearly perfect ring around the galaxy, with a diameter of approximately 50,000 light-years, and a width varying between 500 and 700 light-years. When astronomers analyze this dust using spectroscopy, a technique that splits light into its component wavelengths, they discover a remarkably rich chemical composition. The dust particles themselves are primarily made up of silicates, similar to the minerals that make up much of Earth's crust, and various forms of carbon, including graphite and amorphous carbon. These tiny particles range in size from molecules to grains a few micrometers across, still smaller than a human hair, but giants compared to individual atoms. Perhaps most intriguing is the presence of polycyclic aromatic hydrocarbons, PAHs, within the dust lane. These complex organic molecules consist of multiple rings of carbon atoms with hydrogen atoms attached to their edges. On Earth, we typically associate these compounds with combustion processes, finding them in things like soot and vehicle exhaust. In space, they form through different processes and are actually among the most common carbon-bearing molecules in the universe. Some scientists speculate that these compounds may have played a role in the development of life on Earth, as they contain the carbon-based structures that serve as building blocks for more complex organic molecules. The dust lane also contains a variety of ice formations coating the dust grains. These aren't just water ice, but also frozen carbon monoxide, carbon dioxide, methane, ammonia, and more complex molecules. These ice mantles form when gas molecules in the cold interstellar environment stick to dust particles and freeze. Under certain conditions, these ice coatings can serve as tiny chemical laboratories where reactions occur that wouldn't be possible in the gas phase, potentially creating even more complex molecules. Hydrogen gas permeates the entire dust structure, existing in both molecular form, H2, and atomic form. This hydrogen, along with lesser amounts of helium, makes up the bulk of the gas component in the dust lane. Heavier elements like oxygen, carbon, nitrogen, and iron, elements astronomers collectively refer to as metals, are present in much smaller quantities, but play crucial roles in the chemistry and physics of the region. What makes the Sombrero's dust lane particularly valuable for scientific study is its orientation relative to Earth. Because we view the galaxy nearly edge-on, the dust lane appears as a sharply defined feature against the bright galactic bulge. This allows astronomers to study the dust's properties in exceptional detail, measuring how it absorbs light of different wavelengths and using that information to determine its composition, density, and distribution. The origin of this material tells an important story about stellar evolution and galactic recycling. Most of the elements heavier than hydrogen and helium in the dust lane were forged inside stars through nuclear fusion and then ejected into space when those stars died, either through gentle stellar winds from aging red giants or violent supernova explosions. This enriched material then mixed with the interstellar medium, eventually coalescing into the dense regions we now observe as the dust lane. Despite its dark appearance in visible light, the dust lane transforms dramatically when viewed in other wavelengths. In infrared observations, regions that appear completely dark in optical images suddenly glow with activity. This infrared emission comes from dust grains being heated by starlight and then re-radiating that energy at longer wavelengths. These observations reveal that the dust lane isn't merely a static structure but contains regions of active star formation, where the dense material is collapsing under gravity to form new stars. The dust in the Sombrero galaxy doesn't just absorb light, it also polarizes it. As light from background stars passes through the dust lane, the dust particles align with the galaxy's magnetic field, causing the light waves to oscillate predominantly in certain directions. By measuring this polarization, astronomers can map the magnetic field structure within the galaxy. These observations reveal that the magnetic fields in the Sombrero galaxy generally follow the spiral pattern of the disk, helping to maintain the integrity of the dust lane against disruptive forces. Chemical reactions occurring within the dust lane create a constantly evolving molecular ecosystem. When ultraviolet radiation from nearby hot stars strikes the dust, it can break apart existing molecules and initiate chains of chemical reactions that produce new compounds. Some regions within the dust lane are shielded from this radiation, allowing more fragile molecules to survive and more complex chemistry to develop. This creates a varied chemical landscape across the dust lane, with different regions hosting different molecular species. The detailed study of the Sombrero's dust lane provides valuable insights into similar structures in other galaxies, including our own Milky Way. The processes of star formation, elemental enrichment and chemical evolution observed in the Sombrero likely mirror those occurring throughout the universe. By studying this particularly well-defined example, astronomers gain a better understanding of fundamental cosmic processes. The dynamics of the dust lane also tell us about the galaxy's history and evolution. Computer models suggest that the remarkably uniform and symmetric appearance of the Sombrero's dust lane indicates a galaxy that has evolved without major disruptive events for billions of years. If the galaxy had experienced a recent merger or close encounter with another galaxy, we would expect to see distortions, warps, or asymmetries in the dust lane. Looking at the dust lane of the Sombrero galaxy, we're actually seeing light that has travelled for approximately 28 million years to reach Earth. This means we're observing the galaxy as it existed 28 million years in the past. Over such vast timescales, even this apparently stable structure is slowly evolving. Stars are forming from the dust, adding their light to the galaxy while simultaneously consuming the very material that makes the dust lane visible to us. Unraveling the mysteries of the Sombrero galaxy's distinctive features requires an impressive array of observational techniques and advanced technologies. Astronomers use a diverse toolkit to study this distant galaxy, combining data from multiple wavelengths and various instruments to build a comprehensive understanding of its nature. Each technological advancement has peeled back another layer of the Sombrero's mysteries, revealing new details about its structure, composition, and evolution. Perhaps the most basic but still essential tool for studying the Sombrero galaxy is optical astronomy, observing the light visible to human eyes. Ground-based optical telescopes ranging from modest amateur instruments to giant professional observatories like the Very Large Telescope in Chile have been trained on the Sombrero for decades. Even with moderate-sized telescopes, the galaxy's distinctive shape is apparent, though the finest details remain blurred by Earth's turbulent atmosphere. To overcome atmospheric limitations, astronomers rely heavily on space-based observatories, with the Hubble Space Telescope providing the most iconic images of the Sombrero galaxy. Launched in 1990, Hubble's position above Earth's atmosphere allows it to capture exquisitely detailed images free from atmospheric distortion. Its observations of the Sombrero reveal fine structure in the dust lane, resolve individual bright stars and star clusters, and show the smooth stellar distribution of the central bulge with unprecedented clarity. But visible light tells only part of the story. The Sombrero galaxy, like all celestial objects, emits and absorbs radiation across the entire electromagnetic spectrum. Radio telescopes like the Very Large Array in New Mexico and the Atacama Large Millimeter/Submillimeter Array ALMA in Chile detect emissions from cold hydrogen gas and dust in the galaxy, mapping the distribution of these materials and measuring their motion through the Doppler effect. These observations have revealed rotation patterns in the disk and helped measure the galaxy's total mass. At the opposite end of the spectrum, X-ray observatories like NASA's Chandra and the European Space Agency's XMM Newton detect high-energy emissions from the hottest and most energetic regions of the galaxy. These observations have been crucial in studying the supermassive black hole at the Sombrero's center, revealing hot gas being accelerated to tremendous speeds as it falls toward the event horizon. X-ray observations also detect emissions from binary star systems containing neutron stars or stellar mass black holes, as well as the hot gas ejected by supernova explosions. Infrared astronomy has been particularly valuable for studying the Sombrero's dust components. Observatories like the Spitzer Space Telescope and the James Webb Space Telescope can peer through the dust that appears opaque in visible light, revealing the structure and composition of the dust itself. Infrared observations show warm dust glowing from the absorption of starlight, revealing regions of star formation hidden from optical telescopes. Different infrared wavelengths trace dust at different temperatures, providing a thermal map of the galaxy. Ultraviolet observations, primarily from the Galaxy Evolution Explorer (GALEX) satellite, highlight the galaxy's youngest and hottest stars. which emit strongly in ultraviolet light. The relative scarcity of ultraviolet emission from the Sombrero compared to other spiral galaxies indicates a lower rate of current star formation, suggesting the galaxy has entered a more quiescent phase of its evolution. Spectroscopy is perhaps the most powerful technique in the astronomer's arsenal. By splitting light into its component wavelengths, spectroscopy reveals the chemical fingerprints of elements and compounds in the galaxy. Each element absorbs and emits light at specific wavelengths, creating a unique spectral signature. Spectroscopic observations of the Sombrero galaxy have mapped the distribution of various elements, revealed the motion of stars and gas through Doppler shifts, and measured physical properties like temperature and density in different regions. Advanced spectroscopic techniques like integral field spectroscopy take this a step further by capturing spectra for thousands of points across the galaxy simultaneously, creating three-dimensional data cubes that contain both spatial and spectral information. This allows astronomers to map properties like stellar age, chemical composition, and velocity across the entire galaxy, revealing patterns that help unravel its formation history. Polarimetry, measuring the orientation of light waves, provides yet another window into the Sombrero's physics. As light passes through regions with magnetic fields, its polarization is affected in ways that allow astronomers to map the strength and direction of these otherwise invisible fields. Polarization studies have revealed the magnetic structure of the Sombrero's disk, showing how these fields might influence the motion of gas and the formation of stars. Computer modeling and simulation have become increasingly important tools as well. By creating virtual galaxies in sophisticated simulations, astronomers can test theories about how structures like the Sombrero formed and evolved. These models incorporate our understanding of gravity, fluid dynamics, radiative transfer, and other physical processes to predict how galaxies should appear and behave. When simulations produce results that match actual observations of the Sombrero, it suggests the underlying physics is well understood. Data processing techniques have also revolutionized our ability to extract information from observations. Adaptive optics systems on ground-based telescopes use deformable mirrors to correct for atmospheric distortion in real time, approaching the clarity of space-based observations. Image stacking combines multiple exposures to reveal faint features that would be invisible in single images. Sophisticated algorithms remove instrumental artifacts and enhance contrast to bring out subtle details in the galaxy's structure. Looking toward the future, planned observatories promise even more detailed views of the Sombrero galaxy. The Virasi Rubin Observatory, DOT, with its 8.4-meter mirror and 3.2 gigapixel camera, will conduct repeated surveys of the entire visible sky, potentially revealing variable phenomena in the Sombrero that change over time. Meanwhile, the next generation of extremely large telescopes, with primary mirrors 30 meters or larger, will resolve features in the galaxy that are currently beyond our reach. As these advanced observational technologies continue to enhance our understanding of distant galaxies, it's natural to wonder how the Sombrero galaxy compares to our cosmic home, the Milky Way. Despite both being classified as spiral galaxies, the Sombrero and the Milky Way represent remarkably different evolutionary paths and structural configurations. Comparing these two stellar metropolises reveals fascinating insights about the diversity of galaxy formation and evolution. In terms of basic dimensions, the Sombrero and the Milky Way aren't dramatically different. The Sombrero's disk spans approximately 50,000 light-years in diameter, somewhat smaller than the Milky Way's 100,000 light-year expanse. However, when it comes to mass, the Sombrero outweighs our galaxy substantially. Astronomers estimate the Sombrero's mass at around 800 billion solar masses, compared to the Milky Way's 500 to 600 billion solar masses. This extra mass is concentrated primarily in the Sombrero's central bulge and its exceptionally rich population of stars. The most obvious structural difference between the two galaxies is the size and prominence of their central bulges. The Sombrero galaxy has an enormous elliptical bulge that dominates its appearance, containing most of the galaxy's stars and extending far above and below the galactic disk. But our Milky Way, in contrast, has a relatively modest bulge that's actually shaped more like a rectangular bar than a sphere, extending only about 16,000 light-years across, roughly one-third the diameter of the galaxy's disk. This difference in bulge size reflects fundamentally different evolutionary histories. The Sombrero's massive bulge suggests either an early formation period characterized by intense star formation or a history of mergers with other galaxies that contributed additional stars to the central region. The Milky Way, with its smaller bulge and more prominent disk, likely experienced a more gradual assembly process with fewer major mergers disrupting its disk structure. Star formation presents another striking contrast between these galaxies. The Milky Way continues to form new stars at a moderate rate of about 1 to 2 solar masses per year, primarily within its spiral arms where gas and dust are concentrated. The Sombrero, however, shows minimal ongoing star formation, with rates estimated to be at least 10 times lower than in our galaxy. This quiescence is evident in the Sombrero's colour. It appears yellower and redder than the Milky Way would if viewed from outside, reflecting an older stellar population with fewer hot, blue, young stars. The supermassive black holes at the centres of these galaxies also differ dramatically in scale. The Milky Way's central black hole, Sagittarius A star, has a relatively modest mass of about 4 million times that of our Sun. The Sombrero's central black hole, as mentioned earlier, weighs in at approximately 1 billion solar masses, over 200 times more massive. This enormous difference suggests that the Sombrero's black hole experienced a much more substantial growth history, possibly through multiple mergers with other black holes or more efficient accretion of surrounding matter. The population of globular clusters represents yet another area of contrast. While the Milky Way hosts approximately 150 of these ancient star clusters, the Sombrero boasts around 2,000, an extraordinary number that ranks among the highest for galaxies of its size. This wealth of globular clusters suggests that the Sombrero formed in an environment with abundant gas and dust in the early universe, allowing for prolific star cluster formation, or that it has acquired many clusters through galaxy mergers throughout its history. The spiral structure of these galaxies also differs significantly. The Milky Way has well-defined spiral arms containing concentrations of young stars, gas, and dust that stand out distinctly against the background of older stars. The Sombrero's spiral structure is much more subtle and tightly wound, with less contrast between the arms and interarm regions. This difference reflects the Sombrero's more mature evolutionary state, where star formation has largely ceased and the dynamic processes that create prominent spiral arms have weakened. Another key difference lies in the galaxy's environments. The Milky Way is part of the Local Group, a modest galaxy cluster dominated by our galaxy and the Andromeda Galaxy, with dozens of smaller satellite galaxies orbiting these two major members. The Sombrero, meanwhile, lies on the outskirts of the Virgo cluster, a much larger collection of galaxies, but doesn't appear to be strongly interacting with any neighbouring galaxies currently. This relative isolation may have allowed the Sombrero to maintain its remarkably symmetric appearance. The composition and distribution of gas also differ between these cosmic neighbours. The Milky Way contains abundant cool hydrogen gas throughout its disk, providing fuel for ongoing star formation. The Sombrero, while still containing significant amounts of gas, has much of it concentrated in the dust lane, with relatively little dispersed throughout the rest of the galaxy. This distribution, combined with the stabilizing influence of its massive bulge, helps explain the Sombrero's low star formation rate. When examining the stellar populations, astronomers find that the Sombrero contains a higher proportion of older stars than the Milky Way. Spectroscopic studies reveal that most of the Sombrero's stars formed over 8 billion years ago, with relatively little star formation in the intervening time. The Milky Way shows evidence of multiple distinct episodes of star formation throughout its history, including significant activity within the last billion years. This difference suggests that the two galaxies followed different evolutionary trajectories, with the Sombrero experiencing an intense early period of star formation followed by relative quiescence, while the Milky Way has maintained a more consistent star-forming activity. The dust content also differs markedly between the two galaxies. While the Milky Way's dust is distributed throughout its spiral arms, creating the patchy appearance of the night sky's Milky Way band, the Sombrero concentrates most of its dust in the prominent lane that encircles the galaxy. This clean separation between the dusty disk and the relatively dust-free bulge creates the Sombrero's distinctive appearance, but also indicates different dynamics governing the distribution of interstellar matter. Studying these differences doesn't just satisfy astronomical curiosity, it helps scientists understand the range of possible evolutionary paths for spiral galaxies. The Sombrero may represent the future fate of galaxies like our Milky Way, as they age, deplete their gas reserves, and experience a decline in star formation. By comparing these galactic neighbours, astronomers can test models of galaxy evolution and better understand the processes that shape these immense stellar systems throughout cosmic history. Beyond its scientific significance, the Sombrero galaxy has achieved something rare for an astronomical object. It has become a cultural icon, recognised far beyond the community of professional astronomers. Since its distinctive shape was first noted by Lord Rosse in the 19th century, this galaxy has captured the human imagination and found its way into various aspects of art, literature, education, and popular culture. The striking visual appeal of the Sombrero galaxy has made it one of the most frequently photographed deep sky objects, appearing on countless book covers, websites, and documentary films about astronomy. Its instantly recognizable silhouette, the bright central bulge crossed by the dark dust lane, has become a visual shorthand for the beauty and majesty of the cosmos. Professional astrophotographers consider capturing a detailed image of the Sombrero a significant achievement, while even amateur astronomers with modest equipment can recognize its distinctive shape through their telescopes. In educational contexts, the Sombrero galaxy frequently serves as a gateway to discussions about galactic structure. Its clearly defined components, bulge, disk, dust lane, and halo, make it an ideal teaching tool for explaining how galaxies are organized. Elementary school science textbooks often feature the Sombrero alongside other iconic astronomical images like Saturn's rings or the Eagle Nebula, introducing young students to the wonders of deep space. Museum planetarium shows regularly highlight the Sombrero when discussing galaxy types, using its dramatic appearance to maintain audience engagement with complex astronomical concepts. The galaxy's distinctive name has helped cement its place in popular culture. The comparison to a Mexican sombrero hat is immediately understandable even to those with no astronomical background, creating an accessible mental image that sticks in the memory much more effectively than its official designation as M104 or NGC 4594. This accessibility has made the Sombrero one of the few galaxies outside our own that many people can identify by name. In science fiction, the Sombrero galaxy often appears as a setting for advanced alien civilizations or cosmic phenomena. Its distance from the Milky Way, approximately 28 million light-years, places it far enough away to seem exotic and mysterious, yet close enough, in cosmic terms, to be conceivably reached by fictional faster-than-light spacecraft. Authors and screenwriters have used this relative proximity to situate adventures and first contact scenarios in a location that real-world audiences might recognize. Several notable science fiction novels have placed their stories in or around the Sombrero galaxy. These works often use the galaxy's distinctive appearance as a plot element, with civilizations developing around or specifically because of its unusual structure. The galaxy's relative isolation from major galaxy clusters makes it an attractive setting for stories about civilizations that have developed independently from those in the densely packed regions of the universe. The sombrero has also inspired artists working in various media. Abstract painters have created works based on its interplay of light and shadow, while digital artists frequently incorporate its image into cosmic landscapes and speculative visualizations of space travel. Sculptors have crafted three-dimensional representations of its distinctive profile for science museums and astronomical installations, allowing visitors to appreciate its structure from multiple angles. In the realm of public outreach, the Sombrero Galaxy has become an ambassador for astronomy, appearing on promotional materials for observatories, planetariums, and space science centres. Its image has adorned posters announcing public viewing nights at observatories, encouraging people to look through telescopes and experience the wonders of the night sky firsthand. The galaxy's photograph often appears on the websites of amateur astronomy clubs, inviting newcomers to join and learn more about the cosmos. Philatelists and numismatists might recognize the Sombrero Galaxy from its appearances on postage stamps and commemorative coins from various countries. These issues typically celebrate significant astronomical discoveries or anniversaries of space exploration milestones. The galaxy's distinctive profile makes it recognizable even in the small format of a stamp, allowing it to effectively represent the grandeur of deep space astronomy. In digital media, the Sombrero Galaxy has found new audiences through social media platforms where astronomical images are widely shared and appreciated. High-resolution images from the Hubble Space Telescope and other advanced observatories regularly generate thousands of interactions when posted online, introducing the galaxy to people who might otherwise never encounter astronomical imagery. These shares often prompt discussions about space, science, and humanity's place in the cosmos among general audiences. Video games set in space frequently include the Sombrero Galaxy among their visitable locations. Space exploration and simulation games often recreate its distinctive appearance with varying degrees of scientific accuracy, allowing players to virtually visit and sometimes even navigate through a digital recreation of the galaxy. These interactive experiences help familiarize new generations with the galaxy's structure and place in the universe. Commercial products with space themes, from coffee table books to clothing, wall art to mobile phone cases, frequently feature the sombrero's elegant profile. It's balanced. Symmetrical shape works well in graphic design applications, making it a favorite choice for products aimed at astronomy enthusiasts. Unlike some astronomical images that require explanation to be appreciated, the sombrero's visual appeal is immediate and requires no scientific background to recognize its beauty. The galaxy has even influenced architectural designs, with several observatories and planetariums incorporating elements inspired by the sombrero's profile into their structures. These buildings use the galaxy's recognizable shape to signal their astronomical purpose, creating an immediate visual connection between the facility's function and one of astronomy's most famous objects. The cultural impact of the Sombrero Galaxy exemplifies how certain astronomical discoveries transcend their scientific significance to become part of our shared cultural heritage, like the rings of Saturn or the craters of the Moon. The sombrero's distinctive appearance has made it a cosmic landmark, recognized and appreciated by people who may know very little else about astronomy. This cultural penetration helps maintain public interest in and support for astronomical research, creating a virtuous cycle where scientific discovery and cultural appreciation reinforce each other. Beyond its cultural influence, the Sombrero Galaxy has played a pivotal role in the scientific history of astronomy, challenging and advancing our understanding of the cosmos in numerous ways. When astronomers first began studying this distinctive celestial object, they had no concept of what galaxies truly were. The scientific journey from seeing the sombrero as a mere nebula to recognizing it as a vast island universe of stars has paralleled the broader development of our cosmic understanding. The sombrero's scientific significance began in the late 18th century when Pierre Méchain and Charles Messier first catalogued it. At this time, astronomers had no means of determining the true nature or distance of such objects. The Messier catalogue was actually created to help comet hunters avoid wasting time on stationary fuzzy objects like the Sombrero. This humble beginning as a nuisance in comet hunting belies the galaxy's eventual importance in astronomical discovery. By the mid-19th century, the improved telescopes of astronomers like Lord Rosse revealed the Sombrero's distinctive shape, but the debate about the nature of these spiral nebulae was just beginning. Some scientists believed they were relatively nearby gas clouds within our own galaxy, while others suspected they might be distant island universes, separate galaxies like our Milky Way. The Sombrero, with its clear and distinctive structure, became an important object in this debate. The controversy wasn't settled until the 1920s, when Edwin Hubble used Cepheid variable stars to determine that the Andromeda Nebula was far too distant to be part of the Milky Way. This revolutionary discovery established that spiral nebulae like the Sombrero were indeed independent galaxies, a finding that dramatically expanded our conception of the universe. Although Hubble didn't specifically measure the Sombrero's distance in this work, his findings applied to all spiral nebulae, fundamentally changing how astronomers viewed the Sombrero and similar objects. Once established as a galaxy, the Sombrero became a crucial test case for developing theories of galactic structure and evolution. Its edge-on orientation offered a perfect profile view of its components, clearly showing the relationship between bulge, disk, and halo. When Edwin Hubble developed his famous tuning fork diagram for classifying galaxies in 1926, the Sombrero's distinctive structure made it an important reference point, representing galaxies with prominent bulges and tightly wound spiral arms. The Sombrero also played a significant role in early studies of galactic rotation. In the 1940s and 50s, astronomers began measuring the Doppler shift of light from different parts of galaxies to determine their rotation speeds. The Sombrero's edge-on orientation made it ideal for these studies, as one side of the disk moves toward us while the other moves away, creating a clear signature in the spectroscopic data. These rotation measurements provided some of the first evidence that galaxies are dynamic, rotating systems rather than static structures. By the 1970s, improved spectroscopic techniques allowed more precise measurements of the Sombrero's rotation curve, the relationship between orbital velocity and distance from the galactic center. These measurements revealed a surprising pattern. Stars and gas in the outer regions were moving much faster than could be explained by the visible mass of the galaxy. This discrepancy provided compelling evidence for the existence of dark matter, an invisible form of matter detectable only through its gravitational effects. The Sombrero was among the first galaxies where this effect was clearly documented, contributing to one of the most profound discoveries in modern cosmology. The galaxy's unusually large central bulge and supermassive black hole also made it important in developing theories about the relationship between these galactic components. Studies of the Sombrero in the 1990s helped establish that the mass of a galaxy's central black hole correlates with the mass of its bulge, a relationship that suggests these components evolved together. The Sombrero's extreme bulge-to-disk ratio and exceptionally massive black hole represented an important data point at the upper end of this relationship, helping define its limits. The extraordinary population of globular clusters around the Sombrero has provided crucial insights into how these ancient star systems form and evolve. The sheer number of clusters, approximately 2,000, gives statisticians enough data points to identify patterns and relationships that wouldn't be apparent in galaxies with fewer clusters. Studies of these globular clusters have helped establish their ages, compositions, and orbital properties, contributing to our understanding of the earliest epochs of galaxy formation. With the advent of space-based telescopes, particularly Hubble, the Sombrero became an important target for demonstrating these instruments' capabilities. The iconic Hubble image of the Sombrero, captured in 2003, didn't just produce a beautiful picture, it provided unprecedented detail about the galaxy's structure. revealing features like dust filaments in the disk and individual bright stars that had never been seen before. These observations allowed more sophisticated analysis of the galaxy's components and history than had previously been possible. The Sombrero's significance continues in modern astronomical research. Its relatively clean separation between components, bulge, disk, and halo makes it an ideal laboratory for studying how these elements interact. Its intermediate position between spiral and elliptical galaxy types provides insights into how galaxies transform from one type to another over cosmic time. Its massive black hole offers opportunities to study extreme gravitational environments and accretion processes. Perhaps most importantly, the Sombrero galaxy exemplifies how astronomical objects gain scientific significance through accumulated study over time. Each generation of astronomers has built upon previous knowledge, using new technologies to extract more information from this remarkable galaxy. What began as simply another entry in Messier's catalogue of non-comets has become a crucial reference point for theories of galaxy formation, dynamics, and evolution. The scientific history of the Sombrero galaxy mirrors the development of extragalactic astronomy itself, a journey from simple observation to profound understanding of some of the largest structures in our universe. Among the most fascinating aspects of the Sombrero galaxy revealed through this scientific journey is the extraordinary amount of dark matter it contains. This invisible substance, which doesn't interact with light or other electromagnetic radiation but exerts gravitational pull, dominates the total mass of the galaxy and shapes its dynamics in fundamental ways. Understanding dark matter in the Sombrero gives us crucial insights into one of the most mysterious components of our universe. The first evidence for dark matter in the Sombrero came from studying its rotation curve, the relationship between the orbital velocity of stars and gas and their distance from the galactic center. According to the basic laws of gravity, objects farther from the center should orbit more slowly, just as the outer planets in our solar system move more slowly than the inner ones. However, measurements of the Sombrero in the 1970s and 80s revealed something surprising. After an initial rise, the rotation speed remains nearly constant far out into the galaxy's disk, rather than declining as expected. This flat rotation curve can only be explained if there's substantially more mass in the galaxy than we can see. If we accounted only for visible stars, gas, and dust, the outer regions of the Sombrero would orbit much more slowly than observations show they actually do. The discrepancy is dramatic. Calculations suggest that visible matter accounts for only about 10 to 15% of the total mass needed to explain the observed rotation. The remaining 85 to 90% must be in some invisible form, what astronomers call dark matter. Mapping the distribution of this dark matter in the Sombrero has been a major focus of research. Unlike normal matter, which concentrates in the visible disk and bulge, dark matter appears to form a roughly spherical halo extending far beyond the visible galaxy. This halo may reach out to distances of hundreds of thousands of light years, many times larger than the visible disk. The density of dark matter appears highest toward the center of the galaxy and gradually decreases with distance. But even in the outermost regions measured, it still dominates the mass budget. Several independent methods have confirmed the presence of this dark matter halo. Beyond rotation curves, astronomers have studied the motion of the Sombrero's globular clusters, which orbit far from the galactic center and are therefore excellent probes of the gravitational field at large distances. The velocities of these clusters can only be explained if they're moving in the gravitational field of a much more massive galaxy than what we can see. Similarly, measurements of the temperature of hot gas in the galaxy's outer regions, detected through its X-ray emissions, indicate it's being held in place by the gravitational pull of much more mass than is visible. The exact nature of dark matter in the Sombrero and throughout the universe remains one of the biggest mysteries in modern physics. Scientists have proposed various candidates for what dark matter might be. ranging from exotic subatomic particles that rarely interact with normal matter to primordial black holes formed in the early universe. So far, none of these candidates has been definitively detected, despite sophisticated experiments on Earth designed specifically to catch dark matter particles. The distribution of dark matter in the Sombrero offers potential clues about its nature. Computer simulations of galaxy formation that incorporate different dark matter models produce different predictions about how dark matter should be distributed. By carefully mapping the Sombrero's dark matter distribution and comparing it to these models, astronomers hope to narrow down the possibilities for what dark matter actually is. One particularly interesting feature is the relationship between the dark matter halo and the central supermassive black hole. Some theories suggest a connection between these components, with the growth of one influencing the other. The Sombrero's exceptionally massive black hole, approximately 1 billion solar masses, and extensive dark matter halo make it an excellent test case for these theories, if such a connection exists. The extreme properties of the Sombrero should make the effects more noticeable than in more typical galaxies. The interaction between dark and visible matter also influences the galaxy's evolution. Dark matter played a crucial role in the formation of all galaxies, including the Sombrero, by providing the gravitational wells that drew in normal matter during the early universe. The particular distribution of dark matter around the Sombrero shaped how the visible galaxy assembled, influencing everything from its overall size to the details of its spiral structure. Even today, dark matter continues to affect the galaxy's evolution. It stabilizes the orbital motion of stars in the outer disk, preventing them from flying off into intergalactic space despite their high velocities. It influences how gas flows within the galaxy, potentially affecting star formation rates and patterns. If the Sombrero eventually interacts with or merges with another galaxy, the dark matter halos will interact first, altering the trajectories of both visible galaxies long before they physically collide. Studying dark matter in the Sombrero has broader implications for cosmology. Dark matter appears to be ubiquitous throughout the universe, making up about 85% of all matter and about 27% of the total energy content of the cosmos. Understanding how dark matter behaves in well-studied galaxies like the Sombrero helps scientists refine models of how structure formed in the early universe and how it will continue to evolve in the future. The techniques developed to study dark matter in the Sombrero are being applied to other galaxies as well, building a comprehensive picture of dark matter distribution throughout the universe. Each galaxy offers a slightly different perspective, like pieces of a puzzle that together reveal the larger picture. The Sombrero, with its clear structure and orientation, provides one of the cleaner measurements, serving as a reference point for more complex cases. The search for dark matter connects the study of extremely large structures like the Sombrero galaxy with the hunt for extremely small particles in Earth-based laboratories. Particle physicists are using powerful accelerators to try creating dark matter particles, while specialized detectors deep underground attempt to catch rare interactions between dark matter and normal atoms. If these experiments succeed in identifying dark matter particles, astronomers will finally be able to explain the invisible scaffold that shapes magnificent structures like the Sombrero galaxy. While dark matter provides the invisible scaffolding that shapes the Sombrero galaxy's structure, understanding this majestic object requires looking back through time to trace its evolutionary history. The Sombrero we see today is the product of billions of years of cosmic evolution, with a formation story that began in the early universe. Astronomers estimate that the Sombrero galaxy formed approximately 12 billion years ago, making it one of the older galaxies in our cosmic neighborhood. This venerable age places its birth in the first couple billion years after the Big Bang, during an epoch when the universe was still taking shape and the first large-scale structures were emerging. Determining the age of a galaxy as distant as the Sombrero presents significant challenges. Unlike stars, where age can often be determined more directly through properties like temperature and luminosity, Galaxies contain stars of many different ages. To unravel the Sombrero's history, astronomers analyze the collective properties of its stellar populations. By examining the colors and spectra of different regions, they can identify the mix of stellar ages present in each part of the galaxy. The oldest stars in the Sombrero reside primarily in its globular clusters and central bulge. Spectroscopic studies of these ancient stellar populations indicate they formed more than 11 billion years ago, containing predominantly low metallicity stars, meaning they have relatively small amounts of elements heavier than hydrogen and helium. This chemical composition is characteristic of stars that formed early in the universe's history, before multiple generations of stars had enriched the interstellar medium with heavier elements through supernovae and stellar winds. The galaxy's evolutionary path appears to have been front-loaded, with an intense period of star formation early in its history that created much of its stellar mass. This period likely lasted several billion years, forming stars at rates hundreds of times higher than what we observe in the Milky Way today. During this early epoch, the proto-Sombrero would have appeared very different from its current state, probably bluer, more irregular in shape, and much more active, perhaps even qualifying as what astronomers call a starburst galaxy. Evidence for this early intense star formation comes from the distribution of stellar ages throughout the galaxy. The central bulge shows signs of having formed in a relatively short period, intense burst of star formation, while the disk appears to have built up more gradually over time. This pattern suggests a scenario where the massive central region formed first, with the disk assembling around it through a combination of gas accretion and minor mergers with smaller galaxies. The Sombrero's unusually large bulge-to-disk ratio offers another clue about its formation history. Most spiral galaxies have more prominent disks relative to their bulges, but the Sombrero's massive bulge dominates its structure. This peculiarity has led some astronomers to suggest that the Sombrero may have experienced a major merger event in its past, perhaps a collision between a spiral galaxy and an elliptical galaxy, or between two large spiral galaxies. Such a merger could explain both the oversized bulge and the relatively subdued spiral structure in the disk. Further evidence for the galaxy's complex history comes from detailed studies of its outer halo. Deep imaging has revealed faint stellar streams, remnants of smaller galaxies that were gravitationally disrupted and absorbed by the Sombrero. These cosmic fossils indicate that the galaxy has grown partly through galactic cannibalism, consuming smaller satellite galaxies throughout its lifetime. Each of these merger events would have contributed additional stars, gas, and dark matter to the growing galaxy, while potentially triggering new rounds of star formation. The Sombrero's massive central black hole has evolved alongside the galaxy itself. Starting perhaps as a seed black hole with a mass of a few thousand solar masses, it grew steadily over cosmic time by accreting gas and merging with other black holes during galaxy collisions. The correlation between the black hole's extraordinary mass, about 1 billion solar masses, and the galaxy's large bulge supports the theory that these components evolved in tandem, each influencing the growth of the other through feedback mechanisms. In more recent cosmic history, meaning the last few billion years, the Sombrero appears to have settled into a relatively quiescent phase. Star formation has declined dramatically, with current rates estimated to be less than 1 solar mass per year across the entire galaxy. This decline is typical of galaxies that have depleted much of their cold gas supply, leaving little fuel for creating new stars. The remaining gas in the dust lane continues to form stars at a slow rate, but this activity is minimal compared to the galaxy's earlier epochs. The current appearance of the Sombrero, with its prominent dust lane and well-defined structure, seems to have been largely established by about 5 billion years ago. Since then, the galaxy has evolved relatively passively, with gradual changes driven by the aging of its stellar population rather than dramatic structural transformations. Stars in the bulge have continued to evolve and die, gradually enriching the galaxy with heavier elements, While the disk has slowly grown thinner and more organized as gravitational interactions among stars dampened out irregularities, the future evolution of the Sombrero will likely continue along this quiet path, at least for the next few billion years. Star formation will continue to decline as the remaining gas is consumed or ejected. The stellar population will gradually redden as massive. Blue stars die out and aren't replaced by new star formation. Over much longer timescales, tens to hundreds of billions of years, the disk structure may gradually dissolve as gravitational interactions cause stars to scatter into more random orbits, potentially transforming the Sombrero into something more resembling an elliptical galaxy. What makes the Sombrero particularly valuable for understanding galaxy evolution is that it may represent a transitional state, a spiral galaxy in the process of evolving toward an elliptical form. Its current properties place it between typical spiral and elliptical galaxies in many classification schemes, suggesting we may be witnessing a relatively rare phase in galactic evolution. By studying the Sombrero in detail, astronomers gain insights into how galaxies transform from one type to another over cosmic time. The environment surrounding a galaxy plays a crucial role in shaping its evolution, influencing everything from its rate of star formation to its overall structure. Unlike many galaxies that exist in dense clusters where interactions are common, the Sombrero galaxy resides in a relatively isolated cosmic neighborhood that has allowed it to maintain its distinctive shape and develop at its own pace. Understanding this environment provides important context for interpreting the galaxy's properties and history. The Sombrero galaxy is located approximately 28 million light-years from Earth in the direction of the constellation Virgo. While it sits near the southern edge of the Virgo cluster, one of the largest and nearest galaxy clusters to us, the Sombrero isn't considered a true member of this cluster. Instead, it occupies a position in what astronomers call the Virgo cluster outskirts, or sometimes the Virgo southern extension. This location places it in a transitional region between the dense cluster environment and the more empty voids of intergalactic space. This semi-isolated position has important implications for the galaxy's evolution. Galaxy clusters like Virgo are crowded environments where galaxies frequently interact, sometimes colliding and merging. These interactions can trigger starbursts, strip away gas, disrupt spiral structures, and generally drive rapid evolution. The Sombrero, by maintaining a respectable distance from the cluster's center, has been largely spared these disruptive influences, allowing it to evolve more gradually and maintain its elegant structure. Despite this relative isolation, the Sombrero doesn't travel through the cosmos completely alone. Detailed observations have revealed a system of satellite galaxies orbiting the Sombrero, smaller galaxies bound by its gravitational pull. Most of these satellites are dwarf galaxies, much less massive than the Sombrero itself, containing perhaps a few 100 million stars compared to the Sombrero's hundreds of billions. These satellite galaxies are difficult to observe due to their low surface brightness and the overwhelming glare from the Sombrero, but improved imaging techniques have identified approximately a dozen confirmed satellites. These satellite galaxies interact with the Sombrero in various ways, and over time, the Sombrero's gravitational pull distorts and eventually disrupts some of these smaller companions, tearing them apart and incorporating their stars into the larger galaxy. This process, known as tidal stripping, creates the faint stellar streams observed in the Sombrero's outer halo. Other satellites may eventually spiral inward and merge completely with the Sombrero, contributing to its growth. The satellite system essentially forms a miniature version of the relationship between the Milky Way and its satellites, like the Magellanic Clouds, beyond its immediate satellite family. The Sombrero exists within the larger cosmic web, the vast network of filaments and voids that forms the largest structure in the universe. The galaxy's position relative to this web affects how matter flows into and around it. Cosmological simulations suggest that galaxies like the Sombrero tend to form at the intersections of filaments in this cosmic web, where the density of matter is higher but not as extreme as in cluster centers. The intergalactic medium surrounding the Sombrero, the diffuse gas that fills the space between galaxies, plays an important role in the galaxy's ongoing evolution. This medium is extremely tenuous, with densities typically less than 1 atom per cubic meter, but it extends throughout intergalactic space and contains a significant fraction of the universe's baryonic normal matter. As the Sombrero moves through this medium, it can accrete some of this gas, providing a modest source of new material to potentially fuel star formation. However, the Sombrero's massive halo of hot gas, detectable through its X-ray emissions, creates a barrier that prevents much of this intergalactic gas from reaching the inner regions of the galaxy. This halo has a temperature of millions of degrees and extends far beyond the visible galaxy. When cooler intergalactic gas encounters this hot halo, it gets heated and ionized, making it difficult for the gas to cool and form stars. This process, sometimes called strangulation, contributes to the galaxy's low rate of star formation by cutting off the supply of fresh gas. The broader region around the Sombrero contains other significant galaxies, though none are close enough for direct interaction at present. The nearest major neighbours are other edge-on spiral galaxies like NGC 4566 and NGC 4313, which share some structural similarities with the Sombrero but are slightly smaller and less massive. These galaxies are still millions of light-years distant from the Sombrero, too far for gravitational interactions to significantly affect their current evolution. When astronomers map the large-scale distribution of galaxies in the region, they find that the Sombrero sits in a relatively low-density environment compared to the core of the Virgo cluster. This lower density means the galaxy experiences less of the environmental pressure that affects cluster galaxies. In dense cluster environments, processes like Ram pressure stripping, where a galaxy's gas is pushed out as it moves through the hot intra-cluster medium, and harassment, frequent high-speed encounters with other galaxies, can dramatically transform galaxies. The Sombrero's more peaceful surroundings have allowed it to retain more of its gas and maintain its well-defined structure. The isolation of the Sombrero also means it's surrounded by a substantial dark matter halo that remains largely intact. In cluster environments, dark matter halos can be partially stripped away during galaxy interactions. But the Sombrero's halo appears to extend smoothly to great distances from the visible galaxy. This extensive dark matter cocoon influences how the galaxy interacts with its environment, affecting everything from the orbits of its satellite galaxies to the accretion of gas from intergalactic space. Looking to the distant future, the Sombrero's environment will continue to influence its evolution. The ongoing expansion of the universe, which is accelerating due to dark energy, will gradually increase the separation between the Sombrero and distant galaxy clusters. Over billions of years, this cosmic expansion will leave the galaxy even more isolated than it is today, further reducing the possibility of significant interactions. This increasing isolation, combined with the depletion of its gas reserves, suggests the Sombrero will gradually transition to an even more quiescent state, with star formation eventually ceasing entirely as it becomes what astronomers call a red and dead galaxy. The increasing isolation of the Sombrero galaxy in an expanding universe relates directly to how we observe and study this magnificent object. Everything we know about this distant galaxy comes to us in the form of electromagnetic radiation, light in its many forms, travelling across millions of light-years of space. The Sombrero emits energy across the entire electromagnetic spectrum, from radio waves to gamma rays, with each wavelength revealing different aspects of the galaxy's nature and activity. When we observe the Sombrero in visible light, the range detectable by human eyes, we see primarily the combined glow of billions of stars. The bright central bulge appears yellowish-white, indicating a population dominated by older, cooler stars similar to our Sun, or slightly cooler. These stars emit most strongly in the yellow, orange, and red portions of the visible spectrum. In contrast, the thin disk appears slightly bluer, suggesting the presence of some younger, hotter stars mixed in with the older population. The dark dust lane is visible precisely because it absorbs this starlight, blocking our view of the stars behind it. Shifting to ultraviolet wavelengths reveals a different picture of the galaxy. Ultraviolet light comes primarily from hot, massive, short-lived stars, the kind associated with recent star formation. Observations from ultraviolet telescopes like NASA's Galaxy Evolution Explorer, GALEX, show that the Sombrero emits relatively little ultraviolet radiation compared to more actively star-forming galaxies. What ultraviolet light is detected comes mainly from scattered regions in the disk, particularly along the outer edges of the dust lane where some limited star formation continues. The central bulge, dominated by older stars, appears much fainter in ultraviolet images than in visible light. At the opposite end of the visible spectrum, infrared observations penetrate the obscuring dust and reveal features hidden from optical telescopes. The dust lane, which appears dark in visible light, glows brightly in infrared wavelengths. This infrared emission comes from dust grains heated by starlight to temperatures of a few tens to hundreds of degrees. The specific wavelengths of infrared light emitted depend on the temperature and composition of the dust. Near-infrared observations, wavelengths just longer than visible red light, reveal the distribution of older, cooler stars that make up the majority of the galaxy's stellar mass, while mid- and far-infrared wavelengths map the dust distribution and temperature. Radio waves from the Sombrero provide yet another perspective on this cosmic structure. Unlike higher-energy forms of radiation, which typically come from hot objects like stars, radio emissions often originate from cooler gas and from high-energy electrons moving through magnetic fields. Radio observations reveal the distribution of cold hydrogen gas throughout the galaxy, particularly concentrated in the disk and dust lane. This cold gas serves as the potential fuel for future star formation. Additionally, radio telescopes detect synchrotron radiation, emissions from electrons spiraling around magnetic field lines, which helps map the galaxy's magnetic structure. Moving to higher energies than visible light, X-ray observations with telescopes like Chandra and XMM Newton reveal the hottest and most energetic environments in the Sombrero. The most prominent X-ray source is the galaxy's center, where material falling toward the supermassive black hole creates a hot, energetic region. X-rays are also emitted by binary star systems containing neutron stars or stellar mass black holes, as well as by extremely hot gas, millions of degrees, that fills much of the galaxy's halo. This diffuse hot gas, visible as extended X-ray emission, provides crucial information about the galaxy's total mass and the interaction between its visible and dark components. At the extreme high-energy end of the spectrum, gamma-ray telescopes occasionally detect emissions from the Sombrero, though these are relatively faint. Gamma rays typically originate from the most energetic processes in the universe, such as matter falling into black holes or particles moving at nearly the speed of light. The relatively low gamma-ray output from the Sombrero confirms that its central black hole is currently in a quiescent phase, not actively consuming large amounts of material. The combination of all these different forms of radiation allows astronomers to construct a comprehensive picture of the Sombrero galaxy. By analysing the spectrum, the precise distribution of light across different wavelengths, astronomers can determine the galaxy's composition, temperature, density, and motion. Spectroscopic observations reveal absorption and emission lines from specific elements and molecules, providing a chemical fingerprint of the galaxy's various components. One particularly important feature in the Sombrero's spectrum is the redshift of its light. As the universe expands, light waves from distant galaxies are stretched to longer wavelengths, shifted toward the red end of the spectrum. By measuring this redshift, astronomers have determined that the Sombrero is moving away from us at approximately 1,000 kilometers per second due to cosmic expansion. This redshift corresponds to a distance of about 28 million light-years. meaning we're seeing the galaxy as it appeared 28 million years ago, a significant span of time in human terms, but just a brief moment in the galaxy's multi-billion-year history. The polarization of light from the Sombrero provides additional information that can't be obtained from intensity measurements alone. When light waves oscillate predominantly in certain directions rather than randomly, the light is said to be polarized. This polarization can occur when light scatters off dust particles or passes through regions with magnetic fields. By measuring the polarization of light from different parts of the galaxy, astronomers can map the structure of magnetic fields threading through the disk and halo. Invisible to direct observation, but crucial for understanding the galaxy's physics. The total luminosity of the Sombrero, the amount of energy it radiates across all wavelengths, is estimated to be approximately 25 billion times the luminosity of our Sun. This enormous output comes primarily from its stellar population of several 100 billion stars. However, this luminosity has likely decreased over time as star formation has declined and the stellar population has aged. Early in its history, during peak star formation periods, the Sombrero might have been several times brighter than it is today, particularly in ultraviolet and blue wavelengths associated with young, massive stars. The variability of the Sombrero's emission also provides valuable information. While the galaxy's overall brightness remains relatively constant on human timescales, certain components do show detectable changes. The region immediately surrounding the central black hole varies in X-ray brightness on timescales of days to years, reflecting changes in the amount of material falling into the black hole. Occasional supernovae, the explosive deaths of massive stars, temporarily increase the galaxy's brightness in specific regions, though rare, with perhaps only one occurring every few centuries in a galaxy like the Sombrero. These events can be detected as new points of light that appear and then gradually fade over weeks or months. Studying the light from the Sombrero isn't just important for understanding this specific galaxy, it contributes to our broader understanding of galactic evolution. By comparing the spectral properties of the Sombrero with those of other galaxies at various distances, and thus various points in cosmic history, astronomers can piece together how galaxies change over time. The Sombrero represents a specific stage in this evolution, a massive spiral galaxy transitioning toward a more quiescent state that helps fill in our picture of the cosmic life cycle. Moving beyond the radiation emitted by the galaxy, we find that the outer regions of the Sombrero hold fascinating clues to its formation and evolution. The galaxy's extended halo contains faint stellar streams, ribbon-like structures of stars that wind through the outer reaches of the galaxy like cosmic rivers. These ethereal features, barely detectable even with the most powerful telescopes, tell dramatic stories of galactic cannibalism and the ongoing assembly of large galaxies through the consumption of their smaller neighbours. Stellar streams form when a smaller galaxy or star cluster is captured by the gravitational pull of a larger galaxy like the Sombrero, as the smaller object orbits the galactic centre. The difference in gravitational force across its diameter creates what astronomers call tidal forces, the same type of forces that cause ocean tides on Earth. These tidal forces gradually stretch the smaller galaxy into an elongated structure, eventually pulling it apart entirely and distributing its stars along its orbital path, creating a stream or trail of stars that can wrap multiple times around the host galaxy. Advanced imaging techniques have revealed several distinct stellar streams in the halo of the Sombrero galaxy. These features are incredibly faint, typically thousands of times dimmer than the night sky as seen from Earth, requiring extremely sensitive instruments and sophisticated image processing to detect. The streams vary in width from a few hundred to a few thousand light-years, while extending tens of thousands of light-years in length. They contain stars that once belonged to dwarf galaxies, small galaxies with perhaps a few million to a few billion stars, that were pulled into the Sombrero's gravitational domain billions of years ago. What makes these streams particularly valuable to astronomers is their composition. The stars in these streams typically formed within their original dwarf galaxies, not in the Sombrero itself, and therefore have chemical compositions that differ from the main galaxy. Spectroscopic analysis reveals that stars in the streams tend to be poorer in heavy elements, what astronomers call metals, than stars of similar age in the main body of the Sombrero. This chemical difference serves as a fingerprint, allowing astronomers to identify which stars originated in now-destroyed satellite galaxies. The orbits of these stellar streams provide crucial information about the distribution of mass within and around the Sombrero, particularly its dark matter halo. The paths taken by the streams are determined by the gravitational field they move through, which is dominated by dark matter in the outer regions of the galaxy. By carefully mapping the positions and velocities of stars in these streams, astronomers can reconstruct the three-dimensional shape and mass of the dark matter halo with greater precision than other methods allow, beyond the visible stellar streams. The Sombrero's halo extends much farther into space. This extended halo consists of extremely diffuse distributions of stars, globular clusters, and hot gas that can reach distances of hundreds of thousands of light years from the galactic center. Unlike the flattened disk of the galaxy, the halo is roughly spherical, enveloping the visible galaxy in a vast, nearly invisible cocoon. The stellar component of the halo is composed primarily of very old stars with low metal content, suggesting they formed early in the universe's history before the interstellar medium had been significantly enriched with heavy elements from previous generations of stars. These halo stars move in largely random orbits around the galactic center, unlike the organized rotational motion of stars in the disk. This randomness reflects the different formation mechanism of the halo, while the disk formed from gas that had settled into a rotating structure. The halo assembled through the gradual accumulation of stars from multiple sources, including both stars that formed in place very early and those acquired through mergers. The globular clusters in the halo represent another important component. While many of these ancient star clusters are concentrated relatively close to the galaxy, some orbit at extreme distances, more than 100,000 light-years from the center. These remote clusters serve as tracers of the gravitational field at these distances, allowing astronomers to measure the galaxy's mass even where visible matter becomes extremely sparse. The distribution of these clusters isn't entirely random. Careful statistical analysis reveals subtle patterns that may reflect ancient structures or accretion events that contributed to the formation of the galaxy. Hot gas in the halo emits primarily in X-ray wavelengths and has temperatures of millions of degrees. This gas likely originates from multiple sources. Some was heated during the initial formation of the galaxy. Some was ejected from the disk by supernovae and stellar winds. And some may have been stripped from satellite galaxies during mergers. The pressure and temperature of this gas decrease with distance from the galactic center, creating a gradient that can be measured with sensitive X-ray telescopes. This gas plays an important role in regulating the galaxy's evolution, as it can cool and fall back into the disk to fuel new star formation, or it can be hot enough to escape the galaxy entirely, carrying away metals produced in stars. The boundary between the Sombrero's halo and intergalactic space is not sharply defined. Rather, the density of stars, gas, and dark matter gradually decreases with distance until it becomes indistinguishable from the surrounding cosmic environment. This diffuse outer region is where the galaxy is still growing, slowly accreting material from intergalactic space and occasionally capturing small satellite galaxies that venture too close. The ongoing processes in this outermost halo connect the Sombrero to the larger cosmic web, the vast network of filaments and voids that forms the basic structure of our universe. The cosmic structures that form the outer halo of the Sombrero galaxy are part of an ongoing cycle of stellar birth and death that has shaped this majestic object throughout its long history. Despite its current appearance as a relatively quiet, mature galaxy, the Sombrero hasn't completely ceased its star-forming activity. While it's far less active than younger, more dynamic galaxies, pockets of stellar nurseries can still be found within its vast expanse, telling the story of a cosmic life cycle that continues even in this aging galactic giant. Most of the star formation currently occurring in the Sombrero galaxy takes place in the outer regions of its disk, particularly along the edges of the prominent dust lane. Here, the conditions are still favourable for the birth of new stars. The process begins with cold molecular clouds, enormous concentrations of hydrogen gas mixed with dust that can span hundreds of light years. When portions of these clouds become sufficiently dense, typically due to compression from shock waves generated by nearby supernovae, spiral density waves, or other disturbances, they begin to collapse under their own gravity. As the material falls inward, it fragments into smaller clumps that continue to contract, eventually becoming hot and dense enough at their cores for nuclear fusion to begin. With this, new stars are born. Evidence from spectroscopic observations indicates that the Sombrero experienced a much more intense period of star formation approximately 8 billion years ago. During this earlier epoch, the galaxy was forming stars at a rate perhaps 50 to 100 times greater than its current pace. This period likely coincided with the assembly of much of the galaxy's disk structure and produced a significant portion of the stars we now observe. The evidence for this ancient starburst comes from analysing the ages and compositions of stars throughout the galaxy, particularly in the disk region, where astronomers find a large population of stars with similar ages dating to this period. Today, the Sombrero forms new stars at a rate of less than 1 solar mass per year across its entire volume, quite modest for a galaxy of its size. For comparison, our Milky Way, despite being less massive overall, currently forms stars at a rate of approximately 1 to 2 solar masses per year. This relative quiescence in the Sombrero reflects its status as a galaxy in the later stages of its evolutionary cycle, having already converted much of its available gas into stars during earlier, more active phases. The cycle of star formation in the Sombrero is regulated by a delicate balance between competing processes. On one hand, the available gas supply is gradually depleted as it's converted into stars. Simultaneously, this gas reservoir is partially replenished through various recycling mechanisms. When massive stars end their relatively brief lives in supernova explosions, they eject large amounts of material back into interstellar space. Similarly, less dramatic but more common stellar processes like stellar winds from aging red giant stars continuously return gas to the interstellar medium. This recycled material, enriched with heavier elements forged within the stars, becomes available for new generations of star formation. However, other processes work against star formation in the Sombrero. The energetic output from the central supermassive black hole, though currently relatively modest, has likely been more significant in the past. When active, the energy from the black hole can heat surrounding gas, preventing it from cooling and collapsing to form stars. Similarly, the collective energy from multiple supernovae can create expanding bubbles of hot gas that temporarily disrupt star-forming regions. The galaxy's substantial bulge also plays a role, as its gravitational effects stabilize the disk against the density waves that typically trigger star formation in spiral arms. Interestingly, different regions within the Sombrero show varying levels of star-forming activity. The central regions, despite containing abundant gas, show minimal star formation. Here, the extreme conditions near the supermassive black hole, including strong gravitational forces, intense radiation, and turbulent gas motions, inhibit the stable collapse of gas clouds needed for starbirth. In contrast, the outer disk, particularly where it intersects with the dust lane, contains most of the galaxy's ongoing star formation. In these regions, conditions are more favourable, gas densities are sufficient, but the disruptive effects from the central regions are diminished by distance. Magnetic fields play a crucial but often overlooked role in this stellar life cycle. The Sombrero, like all galaxies, is threaded with magnetic fields that influence the motion and compression of gas clouds. These fields can either support gas clouds against collapse, temporarily preventing star formation, or help channel material into denser regions, potentially enhancing star birth. Measuring these magnetic fields requires specialized observations of polarized light, which have revealed that the Sombrero's magnetic structure generally follows the large-scale rotation of the galaxy, but contains complex, small-scale features in star-forming regions. The current low rate of star formation in the Sombrero points to its future evolutionary path, as the remaining gas is gradually converted to stars with minimal replenishment. Star formation will continue to decline. Eventually, perhaps within a few billion years, it may cease entirely, transforming the Sombrero into what astronomers call a red and dead galaxy, one where no new stars are being formed and the stellar population consists entirely of aging, reddish stars. This trajectory represents a common evolutionary endpoint for massive galaxies, as they exhaust their gas supplies and transition from actively star-forming spiral galaxies to quiescent elliptical systems. The story of star formation in the Sombrero offers valuable insights into the later stages of galactic evolution. Most galaxies we can easily observe are either actively star-forming spirals or already quiescent ellipticals. The Sombrero, with its ongoing but diminished star formation and hybrid structural characteristics, provides a rare glimpse of a galaxy in transition between these states. By studying how and where stars continue to form in this aging galaxy, astronomers gain understanding of the processes that drive galactic evolution and the ultimate fate of spiral galaxies like our own Milky Way. This transitional nature of the Sombrero galaxy makes it a particularly interesting case when considered within the broader framework of galaxy classification systems. Traditional galactic classification schemes sometimes struggle to neatly categorize this peculiar object, as it exhibits characteristics of multiple galaxy types simultaneously. Understanding where the Sombrero fits within these classification systems provides insight not only into this specific galaxy, but into the entire spectrum of galaxy types and their evolutionary connections. The most widely known galaxy classification system was developed by Edwin Hubble in the 1920s and later refined into what's commonly called the Hubble tuning fork diagram. This system divides galaxies into several main types: ellipticals, lenticulars, dot, and spirals, with barred and unbarred varieties. Elliptical galaxies appear as featureless, football-shaped collections of stars with little gas or dust. Spiral galaxies feature rotating disks with spiral arms and central bulges of varying prominence. Lenticular galaxies represent an intermediate type, with a disk and bulge like spirals but lacking distinct spiral arms. Within this classification framework, the Sombrero galaxy occupies an ambiguous position. Most astronomers classify it as an SE-type spiral galaxy, the designation for spirals with very tightly wound arms and a prominent bulge, or sometimes as an S0/A, suggesting it lies at the boundary between spiral and lenticular types. This uncertainty stems from the Sombrero's unusual features, particularly its extraordinarily large bulge relative to its disk. In typical spiral galaxies, the disk component dominates, containing most of the galaxy's visible matter and extending far beyond the central bulge. In the Sombrero, however, the bulge and disk are nearly equal in their contributions to the galaxy's total light. The bulge extends about 15,000 light-years from the centre, while the disk reaches only slightly farther, to about 25,000 light-years. This approximately 1-to-1 ratio between bulge and disk dimensions is highly unusual and places the Sombrero at an extreme end of the spiral galaxy spectrum. This unusual morphology has led some astronomers to suggest that the Sombrero might be better understood not as a typical spiral galaxy, but as a hybrid or transitional object. Some propose that it represents an intermediate stage in the evolution from spiral to elliptical galaxy, perhaps a spiral galaxy in the process of transforming due to past merger events or internal evolutionary processes. Others have suggested it might actually be an elliptical galaxy that has relatively recently acquired a disk of gas and dust through interaction with another galaxy, leading to its current hybrid appearance. Adding to this complexity, the Sombrero's spiral structure is subtle and difficult to discern compared to classic spiral galaxies like the Whirlpool Galaxy M51. While spiral patterns are definitely present, they're tightly wound and lack the dramatic contrast between arm and interarm regions seen in more typical spirals. This subdued spiral structure further supports the notion that the sombrero represents a late evolutionary stage or transitional form between galaxy types. Recognizing the limitations of the traditional Hubble classification for objects like the sombrero, astronomers have developed more sophisticated classification systems that consider additional parameters. One such approach is the concentration index, a numerical measure of how centrally concentrated a galaxy's light distribution is. The sombrero has an exceptionally high concentration index, reflective of its dominant bulge. Another parameter is the galaxy's colour, which indicates the ages of its stellar populations. The sombrero's relatively red colour, particularly in its bulge, indicates an older stellar population consistent with a galaxy in the later stages of evolution. Modern classification systems also consider kinematics, the motion of stars and gas within the galaxy. The sombrero shows a clear rotational signature in its disk, consistent with spiral galaxies, but also has significant random stellar motions in its bulge, similar to elliptical galaxies. This kinematic duality further emphasizes its transitional nature between classic galaxy types. The prominence of the sombrero's dust lane adds another wrinkle to its classification. Dust lanes are common in spiral galaxies but typically follow spiral arms or other disk features. The sombrero's dust lane forms an almost perfect ring around the galaxy, a relatively unusual configuration that reflects both its nearly edge-on orientation to our line of sight and the actual physical distribution of dust in a relatively uniform ring rather than pronounced spiral arms. The classification challenge presented by the sombrero has actually contributed to the refinement of galaxy classification systems. By studying outlier galaxies that don't fit neatly into established categories, astronomers gain insights into the full spectrum of galaxy types and the evolutionary processes that connect them. The sombrero demonstrates that galaxy evolution isn't a simple linear progression through discrete types, but can produce intermediate forms with characteristics of multiple classifications. The sombrero's hybrid nature also reminds us that galaxy classification is ultimately a human attempt to impose order on what is actually a continuous spectrum of galactic properties. While classification systems are valuable tools for organizing our understanding, nature doesn't always conform to our categorical boundaries. The sombrero, with its blend of spiral and elliptical characteristics, its unusually massive bulge, and its subdued disk, represents a particularly striking example of how galaxies can defy simple classification. Beyond its challenging classification, the Sombrero galaxy contains several puzzling features that continue to intrigue astronomers. Despite decades of detailed observation with increasingly sophisticated instruments, certain aspects of this galaxy defy straightforward explanation or appear inconsistent with our current understanding of galactic physics. These anomalies are particularly valuable to scientists, as discrepancies between observation and theory often point toward new discoveries or refinements in our understanding of cosmic processes. One of the most persistent puzzles involves unusual radio emissions detected from specific regions of the Sombrero galaxy. Radio telescopes have identified several discrete sources that don't correspond to features visible in other wavelengths. These sources emit radio waves with spectral characteristics that don't match typical emission mechanisms like star formation regions, supernova remnants, or active galactic nuclei. Some of these anomalous radio sources appear to change slightly in brightness over periods of months to years, suggesting they're not extended structures but rather compact objects of some kind. Various explanations have been proposed, including unusual types of supernovae, previously unknown classes of stellar remnants, or even more exotic possibilities, but none has been conclusively confirmed. Another puzzling feature involves the galaxy's rotation curve, the relationship between orbital velocity and distance from the galactic centre. While most galaxies show relatively smooth rotation curves, the Sombrero exhibits subtle but definite perturbations, places where stars and gas orbit slightly faster or slower than expected based on standard models. These deviations are too systematic to be measurement errors and suggest either unusual distributions of mass within the galaxy or perhaps modifications to our understanding of how gravity works at galactic scales. Some researchers have suggested these anomalies might be related to the galaxy's unusual formation history, perhaps resulting from past merger events that haven't yet fully stabilized. The Sombrero's globular cluster system presents another anomaly. While the overall number of globular clusters is remarkably high as previously discussed, their distribution around the galaxy shows unexpected asymmetries. There are approximately 15% more globular clusters on one side of the galaxy than the other, a difference too large to occur by random chance. This asymmetry doesn't align with any visible features of the galaxy and remains unexplained. It may indicate a past gravitational interaction with another galaxy that pulled more clusters to one side, but no obvious candidate for such an interaction has been identified in the Sombrero's vicinity. The dust lane itself exhibits some unexpected properties. Detailed spectroscopic analysis has revealed regions within the dust lane where the ratio of different carbon isotopes, carbon-12 to carbon-13, differs significantly from what's observed in most other galaxies. Carbon isotope ratios provide important information about stellar nucleosynthesis and the chemical evolution of galaxies. The unusual ratios in parts of the Sombrero's dust lane suggest either unusual stellar populations or some unknown process affecting the galaxy's chemistry. These anomalous regions are concentrated in the outer portions of the dust lane, possibly indicating they originated from material accreted from outside the galaxy rather than processed internally. Perhaps one of the most significant anomalies is the remarkably low rate of supernovae observed in the Sombrero, given its size and stellar population. Astronomers would expect to detect a supernova in this galaxy approximately once every 50 years on average. However, no supernova have been definitively observed in the Sombrero in modern astronomical history, roughly the past century of systematic observation. This deficiency might indicate our understanding of supernova rates is incomplete, or it might suggest something unusual about the stellar populations in the Sombrero, such as a deficiency of the massive stars that typically produce the most visible supernova. X-ray observations have revealed another puzzling feature: several ultra-luminous X-ray sources that appear too bright to be explained by conventional stellar processes. These discrete sources emit X-rays at rates thousands of times greater than typical X-ray binary systems, where a normal star orbits a neutron star or stellar mass black hole. The nature of these ultra-luminous sources remains debated, with possibilities including intermediate mass black holes, larger than stellar but smaller than supermassive black holes, unusually efficient accretion onto stellar mass black holes, or beamed emission that only appears extraordinarily bright due to its orientation toward Earth. The galaxy's magnetic field structure contains yet another anomaly. Most spiral galaxies exhibit magnetic fields that generally follow the spiral pattern of the disk, but portions of the Sombrero's magnetic field show unusual orientations that appear to go against the overall rotation of the galaxy. These magnetic reversals typically occur in localized regions a few thousand light-years across. Similar features are occasionally seen in other galaxies but are particularly prominent in the Sombrero. Their origin remains unclear but may be related to turbulence in the interstellar medium or the aftermath of energetic events like hypernova explosions. Some of the most intriguing anomalies concern the motion of stars in the galaxy's outer halo. Detailed spectroscopic studies have identified groups of stars moving in ways that don't align with the galaxy's overall rotation. These stars appear to be orbiting in planes tilted with respect to the main disk, or even in retrograde orbits, moving in the opposite direction to the galaxy's rotation. Such misaligned stellar motions typically indicate past accretion events, where stars from a captured dwarf galaxy retain some memory of their original orbital direction. However, the number and distribution of these kinematically distinct populations in the Sombrero's halo are unusual compared to other galaxies of similar size and environment. The central few hundred light-years of the galaxy exhibit another puzzling feature. Despite containing substantial amounts of molecular gas, this region shows virtually no star formation. In most galaxies, where dense molecular gas is present, star formation typically follows. The complete suppression of star formation in this gas-rich central region suggests some unknown mechanism is preventing the gas from collapsing to form stars. Possibilities include unusual turbulence in the gas, stronger than expected magnetic fields providing pressure support against collapse, or subtle effects from the central black hole extending farther than current models predict. These various anomalies make the Sombrero galaxy an especially valuable target for future astronomical studies. They remind us that despite our advanced understanding of galactic physics, there remain aspects of even relatively nearby galaxies that we cannot fully explain with current theories. Each unexplained feature potentially represents an opportunity to refine our models and deepen our understanding of the complex processes that shape galaxies throughout the universe. As observational technologies continue to improve, some of these mysteries will likely be resolved, while new anomalies may be discovered, continuing the cycle of scientific inquiry that drives astronomy forward. These unresolved questions naturally lead us to consider the ultimate fate of this majestic galaxy. What cosmic future awaits the Sombrero over the coming billions and even trillions of years? Astronomers can make reasonable projections about the galaxy's evolution based on our understanding of physics, current observations of the Sombrero's properties, and computer simulations that model galactic evolution over cosmic timescales. While such projections become increasingly uncertain the further into the future we attempt to look, they provide fascinating insights into the life cycles of galaxies and the ultimate fate of these immense stellar systems. In the relatively near cosmic future, the next billion years or so, the Sombrero galaxy will likely continue along its current evolutionary trajectory with only modest changes. Its star formation rate, already low, will continue to decline gradually as the remaining gas in the dust lane is either converted to stars or expelled from the galaxy by stellar winds and supernovae. The galaxy's appearance will slowly change as its stellar population continues to age. As massive, bright, blue stars reach the ends of their relatively short lives without being replaced by new star formation, the galaxy will appear increasingly red and faint. The distinction between the disk and bulge may become less pronounced as the aging disk loses its remaining blue stars and takes on a colour more similar to the already red bulge. Looking ahead a few billion years, the Sombrero may experience interaction with some of its satellite dwarf galaxies. Gravitational forces are gradually drawing these smaller galaxies inward, and eventually, some will likely merge with the Sombrero. These minor mergers wouldn't dramatically alter the galaxy's overall structure, but could trigger localized bursts of star formation as fresh gas is introduced to the system. They might also create visible distortions in the galaxy's outer regions, such as tidal tails or shells of stars, which would gradually dissipate over hundreds of millions of years following each merger event. The central supermassive black hole will continue to exert influence over the galaxy's evolution. While currently in a relatively quiescent state, the black hole may experience periods of increased activity in the future, particularly if gas-rich dwarf galaxies are consumed or if instabilities in the galaxy's gas distribution channel material toward the center. During such active periods, energy output from the central region could heat the surrounding gas, further suppressing star formation and potentially driving gas out of the inner regions of the galaxy. On a timescale of about 5 to 7 billion years, our Milky Way is expected to collide and merge with the neighbouring Andromeda galaxy. While the Sombrero is not on a collision course with any similarly sized galaxy, this massive merger in our local galactic neighbourhood could potentially affect the Sombrero indirectly by altering gravitational forces within the local group and beyond. However, at a distance of 28 million light-years, any such effects would be minimal and would take many additional billions of years to manifest. Looking further ahead, perhaps 10 to 20 billion years from now, the Sombrero will likely have transformed into what astronomers classify as a red and dead elliptical galaxy. Its remaining gas will have been either converted to stars or ejected, leaving no material for new star formation. The distinctive dust lane will have disappeared, as the dust is either incorporated into stars or dispersed by radiation pressure and other forces. The disk component may become less distinct as gravitational interactions between stars cause the orderly rotational motion to gradually transform into more random orbital patterns, without the ongoing formation of new, bright stars to trace its spiral structure. The galaxy would lose its spiral features entirely. On even longer timescales of hundreds of billions to trillions of years, more profound changes await the Sombrero as the universe itself ages. The accelerating expansion of the universe, driven by dark energy, will gradually isolate the Sombrero and other galaxies from one another. Eventually, galaxies outside the local gravitationally bound group will recede beyond the cosmic horizon, becoming permanently unobservable. The Sombrero, relatively isolated even today, will become increasingly alone in an expanding cosmic void. Within this isolated galaxy, stellar evolution will continue its inexorable progress. Low-mass stars like our Sun can shine for tens of billions of years, but eventually, all stars reach the ends of their lives. As the last stars die, first the massive ones, then progressively smaller ones, they'll leave behind white dwarfs, neutron stars, and black holes. These stellar remnants will continue to orbit within the galaxy, occasionally colliding to create transient events like neutron star mergers or new black holes. After trillions of years, what was once the magnificent Sombrero galaxy will consist primarily of these stellar remnants, a ghost galaxy of dead stars orbiting in darkness. Even these remnants will gradually lose energy through gravitational radiation, causing their orbits to decay. Many will eventually fall into the central supermassive black hole, adding to its mass. Others may be ejected from the galaxy through gravitational interactions, scattering into intergalactic space. The supermassive black hole itself, which today weighs about 1 billion solar masses, will gradually grow by consuming stars and gas, potentially reaching many times its current mass. Eventually, after timescales almost beyond comprehension, perhaps 10 to the power of 40 years, even this black hole will begin to evaporate through Hawking radiation, an extremely slow quantum process through which black holes lose mass. This evaporation accelerates as the black hole shrinks, ultimately ending in a final burst of radiation. The ultimate fate of the Sombrero galaxy, like all galaxies, is dissolution, a return of its constituent particles to the cosmic background. Yet this end is so inconceivably distant that countless cycles of cosmic evolution will occur before it is realized. The majestic structure we observe today, with its distinctive hat-like appearance, represents just one brief moment in an epic cosmic timeline stretching from the fiery birth of galaxies in the early universe to their eventual fade into darkness in the far future. This vast temporal perspective emphasizes the remarkable opportunity we have to observe and study galaxies like the Sombrero during the cosmically brief period when they exist in their current splendor. The incomprehensibly distant fate of the Sombrero galaxy may seem purely theoretical, but our ability to make such predictions rests entirely on our capacity to observe and analyze this distant object in the present. The striking images of the Sombrero galaxy that have captivated both scientists and the public represent remarkable achievements in astronomical imaging and visualization techniques. These techniques have evolved dramatically over the decades, transforming how we study and understand this cosmic landmark and similar objects throughout the universe. Creating the iconic images of the Sombrero galaxy involves far more than simply pointing a telescope and taking a picture. Modern astronomical imaging is a sophisticated process that combines advanced optical systems, digital sensors, image processing algorithms, and scientific visualization techniques to reveal details invisible to both the naked eye and even to early astronomical instruments. The journey from photons leaving the galaxy 28 million years ago to the brilliant images we see in publications involves numerous technical innovations and careful scientific decisions. The most recognizable images of the Sombrero come from the Hubble Space Telescope, which has observed this galaxy multiple times since its launch in 1990. Hubble's advantage comes partly from its position above Earth's atmosphere, which allows it to capture images free from the blurring effects of atmospheric turbulence. But equally important is its sophisticated optical system and imaging instruments. When Hubble observes the Sombrero, it typically doesn't capture a single image, but rather a series of exposures through different filters, each allowing only specific wavelengths of light to pass through. Common filter combinations include those isolating blue, green, dot, and red light, approximately corresponding to the colors perceived by human vision. These separate filtered images are then combined in a process called color composition. This isn't as simple as just stacking the images. Scientists must carefully align them to compensate for any slight movement of the telescope between exposures, calibrate them to account for differences in detector sensitivity and exposure time, and then assign colors to each filtered image. While natural color images attempt to represent what the human eye might see if it were as sensitive as the telescope, many astronomical images use false color approaches that assign colors to highlight particular features or to represent light outside the visible spectrum. For the Sombrero galaxy specifically, image processors often enhance the contrast between the bright bulge and the dark dust lane, as this distinctive feature defines the galaxy's famous appearance. This enhancement isn't arbitrary manipulation, but rather a science-based decision to emphasize the galaxy's most significant structural components. The processing must balance aesthetic appeal with scientific accuracy, creating an image that is both visually striking and scientifically informative. Beyond the visible light images familiar to the public, astronomers create visualizations of the Sombrero across the entire electromagnetic spectrum. Radio observations, typically displayed as contour maps overlaid on optical images, reveal the distribution of cold gas throughout the galaxy. X-ray data, dot, often shown in blue or purple hues, highlight the hottest regions, particularly around the central black hole. Infrared imagery, frequently colored in red tones, penetrates the dust lane to reveal the distribution of stars and warm dust hidden from optical telescopes. Combining these multi-wavelength observations creates what astronomers call multispectral or panchronic images, composite views showing structures that would be impossible to see in any single wavelength. These scientific visualizations aren't simply pretty pictures, but powerful analytical tools that allow astronomers to correlate features across different emission mechanisms, revealing relationships between various components of the galaxy. Advanced processing techniques dramatically enhance what telescopes can reveal about the Sombrero. One such technique is deconvolution, a mathematical process that attempts to remove the blurring caused by the telescope's optics and the atmosphere. By understanding precisely how a point source of light, like a single star, gets blurred by the imaging system, algorithms can partially reverse this blurring, revealing finer details in the original object. Applied to the Sombrero, deconvolution has helped resolve individual stars in the galaxy's outer regions and sharpen the boundary between the dust lane and the bulge. Another crucial technique is image stacking or co-addition. By combining many shorter exposures of the same object, astronomers can achieve the same light-gathering power as a single long exposure while minimizing the risk of tracking errors or cosmic ray hits that would ruin a single long exposure. For extremely faint features like the Sombrero's outer halo and stellar streams, stacking dozens or even hundreds of images can reveal structures thousands of times fainter than the night sky background. Specialized software has been developed to identify and extract specific features within galaxy images. Edge detection algorithms help trace the precise boundaries of the dust lane, while pattern recognition software can automatically identify globular clusters or background galaxies. Machine learning approaches are increasingly being applied to astronomical image analysis, with neural networks trained to identify features that might be missed by human observers or traditional algorithms. Three-dimensional visualization techniques have transformed how astronomers conceptualize and communicate the structure of objects like the Sombrero. Though we only see the galaxy from our specific vantage point, combining information about the rotation of the galaxy with models of its likely three-dimensional structure allows scientists to create virtual models showing what the Sombrero might look like from different angles. These models aren't mere artistic renderings, but are constrained by actual observational data. Some visualization systems allow astronomers to fly around these models in virtual reality, gaining intuitive insights about the galaxy's structure that might not be apparent from two-dimensional images alone. Time-based visualization techniques are also important for understanding dynamic processes within the galaxy. By creating simulations based on observed properties, astronomers can model the orbital motion of stars and gas around the galactic center, the gradual evolution of the stellar population, or the effects of past interactions with other galaxies. These simulations can then be rendered as animations that compress billions of years of galactic evolution into minutes, making cosmic timescales comprehensible to human perception. The visualization of data from the Sombrero isn't limited to imagery. Spectroscopic data, measurements of light intensity at many specific wavelengths, are often displayed as graphs showing intensity peaks and troughs that reveal the chemical composition and motion of different regions. More complex spectroscopic datasets that include spatial information are visualized as data cubes, three-dimensional representations where two dimensions correspond to position within the galaxy and the third represents the wavelength or frequency of light. Special software allows astronomers to slice through these data cubes, revealing how spectral features vary across the galaxy's structure. For public outreach and education, these scientific visualizations are often further refined to create the stunning galaxy portraits that appear in publications and online. These images serve dual purposes, communicating scientific information while also inspiring interest in astronomy. The iconic nature of the Sombrero galaxy makes it particularly valuable for such educational visualization, as its distinctive shape is easily recognizable even to those with little astronomical background. The technical challenge of creating these visualizations continues to drive innovation in both astronomy and computer science. New algorithms for image enhancement, novel approaches to data fusion, and increasingly sophisticated rendering techniques all contribute to our ability to extract meaningful information from observations of distant galaxies. As these techniques continue to evolve, our visual understanding of objects like the Sombrero galaxy will likely become even more detailed and comprehensive in the coming years, beyond their immediate scientific and educational value. The sophisticated images and visualizations of the Sombrero galaxy contribute to broader cosmological theories by providing detailed case studies against which theoretical models can be tested. The specific structure, composition, and behavior of this well-studied galaxy offer crucial constraints for our understanding of how galaxies form and evolve within the larger cosmic context. The implications of the Sombrero's characteristics extend far beyond this single object, influencing our understanding of fundamental processes throughout the universe. One of the most significant implications comes from the Sombrero's unusual morphology. particularly its extremely large bulge relative to its disk. Most galaxy formation models suggest that spiral galaxies with prominent bulges formed through a combination of initial collapse and subsequent mergers with other galaxies. The Sombrero structure represents an extreme case that challenges these models to explain how such a massive central bulge could form while still maintaining a relatively intact, orderly disk structure. By adjusting theoretical models to account for galaxies like the Sombrero, astronomers develop more comprehensive theories of galaxy formation that must encompass the full diversity of observed galactic structures. The distribution of globular clusters around the Sombrero provides another important constraint for cosmological theories. The extraordinary number of these ancient star clusters, approximately 2,000, suggests that the early environment in which the Sombrero formed was particularly conducive to creating these dense stellar groupings. This observation helps refine models of star formation in the early universe, when gas densities were higher and chemical compositions differed from today. The spatial distribution of these clusters also traces the galaxy's gravitational potential, providing independent confirmation of models for how dark matter is distributed within and around galaxies. The Sombrero's central supermassive black hole, with its billion solar mass bulk, offers critical insights into the co-evolution of galaxies and their central black holes. Observations across the cosmic landscape have revealed a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. The Sombrero, with its unusually large bulge and correspondingly massive black hole, helps define the upper end of this relationship. This correlation suggests a fundamental connection between black hole growth and galaxy formation, a connection that must be explained by any comprehensive theory of galactic evolution. Current models propose several feedback mechanisms that might maintain this relationship. As a central black hole grows by accreting matter, it releases enormous amounts of energy that can heat surrounding gas, potentially preventing it from cooling and forming stars. This process could regulate both the growth of the black hole and the growth of the galaxy around it. The Sombrero, with its currently low star formation rate despite substantial gas reserves, may demonstrate these feedback effects in action. The star formation history of the Sombrero, with its apparent early burst followed by gradually declining activity, aligns with a cosmological model called downsizing. This model suggests that the most massive galaxies formed the bulk of their stars earlier and more quickly than less massive galaxies. The Sombrero's evolution supports this picture, showing how massive galaxies may have experienced intense early star formation that rapidly consumed or expelled much of their gas, leading to relatively quiescent later stages. Understanding this process helps refine models of how star formation has proceeded throughout cosmic history. The Sombrero's location relative to the Virgo cluster provides context for theories about environmental effects on galaxy evolution, unlike galaxies in dense cluster environments, which often show signs of gas stripping and disruption from interactions with neighbouring galaxies and the intra-cluster medium. The Sombrero's relatively isolated position has allowed it to evolve with minimal external disturbance. This contrast helps clarify which aspects of galactic evolution are driven by internal processes versus external environmental factors. Detailed measurements of the Sombrero's rotation curve, how the orbital velocity of stars and gas varies with distance from the centre, provide crucial constraints for theories of dark matter. The particular shape of this rotation curve implies a specific distribution of dark matter throughout the galaxy. By comparing this inferred distribution with predictions from various dark matter models, astronomers can test competing theories about the nature of this mysterious substance. The Sombrero's well-defined structure and orientation make it a particularly valuable test case for such comparisons. The chemical composition of different regions within the Sombrero offers insights into the production and distribution of elements throughout cosmic time. Spectroscopic measurements reveal how the abundance of heavy elements varies from the galaxy's centre to its outskirts, and between its disk and bulge components. These patterns reflect the history of star formation and the effectiveness of various mixing processes that distribute newly formed elements throughout the galaxy. Such observations help calibrate models of chemical evolution that track how successive generations of stars have gradually enriched the universe with elements heavier than hydrogen and helium. Computer simulations of galaxy formation have become increasingly sophisticated, attempting to model the complex interplay of gravity, gas dynamics, star formation, and feedback processes that shape galaxies over billions of years. The Sombrero Galaxy, with its unusual combination of features, presents a challenging test case for these simulations. When a simulation successfully reproduces a galaxy with the Sombrero's specific characteristics, it suggests that the underlying physical model correctly captures the essential processes of galaxy formation. Conversely, failure to reproduce Sombrero-like galaxies in simulations may indicate missing or incorrectly modelled physical processes. Recent simulations incorporating dark matter, gas dynamics, star formation, and black hole feedback have begun to produce virtual galaxies with some similarities to the Sombrero, suggesting progress in understanding the complex interplay of these factors. However, perfectly reproducing all of the Sombrero's distinctive features remains challenging, indicating that our models of galaxy formation are still incomplete. Perhaps most profoundly, the Sombrero's existence as a massive, well-organized structure that formed relatively early in the universe's history helps constrain cosmological parameters, the fundamental numbers that describe our universe's composition, expansion rate, and evolution. The formation of such large structures requires specific conditions in the early universe, including the right balance between matter, and dark energy, as well as appropriate initial density fluctuations from which galaxies could grow. By studying when and how galaxies like the Sombrero formed, astronomers refine these cosmological parameters, gradually piecing together the fundamental nature of our universe and the cosmic story in which galaxies like the Sombrero and our own Milky Way are both products and participants.